Hey there, ready for a deep dive?
Yeah.
Today we're tackling last passage percolation in hierarchical environments.
Ooh, interesting stuff.
It's all about finding the best path
Okay.
through a random landscape.
Mm-hmm.
But there's a twist.
Right.
The randomness, it has layers, kind of like fractals.
Yeah. It's a fascinating area where probability meets statistical physics.
Really?
And today we'll be looking at two specific types of these landscapes.
Okay.
Ones with heavy-tailed distributions and others, well, they're based on branching random walks.
Heavy tails, branching walks. This sounds pretty complex.
Right.
Could you maybe break it down for us? What kind of landscapes are we dealing with here?
Yeah, for sure. Let's start with that heavy-tailed environment.
Okay.
So picture a landscape. Most points have small values.
Mm-hmm.
But then there's this chance you might run into a huge g-value, a real game changer.
Wow.
The probability of finding these large values, well, it decreases as a power law with exponent 2.
So like rare but impactful.
Exactly. Think of it as a landscape with hidden treasures. Most are small, but, there's a chance of striking gold.
I like that analogy. So it's like playing the lottery while navigating a maze.
Yeah.
What about the branching random walk landscape? What's that like?
Okay, so that one, it's built in layers.
Okay.
Just imagine each point at the base layer has this, random value, right?
All right.
Then you group these points, assign a new random value to each group, and you repeat that process.
So you're saying it's like neighborhoods with similar characteristics?
Exactly. One affluent block might kind of suggest the surrounding ones are well off too.
I see. So then our mission, I guess, is to figure out how these hierarchical structures affect the best path through each landscape.
That's it. We're on the hunt for patterns in this chaos, right?
Okay.
We want to understand these logarithmic corrections that kind of pop up in these critical models.
Sounds intense. Before we jump into all the specifics, maybe we can, level set with some familiar ground. What about those simpler environments? How do they relate to the Kardar-Parisi-Zhang or KPZ universality class?
Great point. Let's look at a classic example. Last passage percolation, or LPP, on a square lattice.
Okay.
In these simpler, well-behaved environments, LPP typically falls into that KPZ universality class.
So this class, this KPZ class, it gives us a framework for understanding how randomness works in different systems.
Precisely. For LPP, KPZ universality, well, it predicts certain characteristics about the fluctuations in the last passage time. The total reward from the best path.
I see.
And the transversal fluctuations of that path.
Okay, so like how much the path wiggles around.
Exactly. The last passage time, it fluctuates around its average by an amount proportional to n to the power of 13.
To the 13.
Yeah, where n is like a measure of how big the system is.
Gotcha. So the fluctuations grow slower than the system size itself.
Exactly. And those transversal fluctuations, they measure how much the optimal path kind of deviates from a straight line.
Right.
They're proportional to n to the power of 23.
Okay, so 13 and 23, these exponents they related somehow.
They are. They're linked by the KPZ scaling relation.
Okay.
This relation helps us understand that trade-off, between getting the most reward and minimizing the path's deviations.
So it's like, try to be efficient, but also explore different options.
You got it. But now, these heavy-tail distributions, they throw a wrench into those neat KPZ predictions.
Really? Why?
Those large values, those occasional ones, they can really impact the optimal path, lead to deviations from what we expect.
Right, like those jackpots, they could cause some serious detours.
Exactly.
So how do we even begin to analyze something that unpredictable?
Well, one way is to use what's called the Flory argument.
Flory argument?
It's a way to predict those fluctuation exponents in these heavy-tailed scenarios.
Okay.
It looks at the interplay between the size of, imagine like a cylinder, around the average path, and the distribution of the rewards.
So we're trying to account for those potential jackpots.
Right.
By looking at the biggest one we might find in a certain area around the average path.
Precisely. Let's say the probability of a reward exceeding a certain value. Let's call it seat. It decays as t to the power of r, where r is our tail exponent. The Flory argument, it suggests the fluctuation exponent for the passage time, let's call that, is equal to 1 plus fc, where r is that transversal fluctuation exponent.
So we have an equation relating Keach and R-Artor.
Right. And it also suggests that the cost of deviating from that average path, which is roughly proportional to r to the power of 2, 1.
Okay.
It should be balanced with the fluctuations from the heavy tail.
All right, so two equations relating those fluctuation exponents are to the tail exponent.
Exactly. Now we can solve these simultaneously
Hmm.
and predict the fluctuation behavior for different values of R.
I see.
And things get really interesting when R equals 2.
Oh, why 2?
Well, it's a critical point that typical KPZ behavior kind of breaks down.
Okay.
And we start seeing these logarithmic corrections.
Critical, like a tipping point where the system just changes drastically.
Yeah, precisely. When poly is 2, the system shows this multi-scale behavior.
Okay.
Similar patterns of randomness, but at different zoom levels.
Interesting.
It's kind of fractal-like. A hallmark of those critical phenomena in statistical physics, often leading to logarithmic corrections in the scaling.
So we've set the stage. We kind of get why this heavy-tailed environment is so challenging.
Right.
What's the first big finding in this paper?
Theorem 1, it establishes a lower bound for that logarithmic correction exponent in this critical OA2 case.
Okay.
It says the last passage time in this environment, it grows at least as fast as n times the logarithm of n to the power of 34.
Wow.
All divided by the logarithm of n.
N times log n to the 34 over log of log n. That's a mouthful.
It is. But the point is, it tells us the passage time grows faster than linearly with n. It shows the influence of those heavy tails.
Right. Those large values, they really mess things up. But how did they get this result? Did they run simulations of these landscapes?
No, they used a multi-scale construction. They built a specific path, a heavy path, with a lot of weight.
So they strategically created a path to take advantage of those big values.
Exactly. But there's a balance. They maximize the points collected at each scale while making sure the path doesn't stray too far from the average path.
So like planning a road trip, you want to see the landmarks, but too many detours make the trip super long.
Exactly. Imagine you divide the landscape into squares, different sizes.
Okay.
The construction starts by picking points with high rewards from those largest squares and connecting them. But there's a constraint on how much the path can deviate from the diagonal.
So picking the best areas and figuring out an efficient route between them.
Right. Then they repeat this process, moving to smaller squares, adding points, keeping that constraint.
Okay.
They analyze the weight collected at each scale, combine the contributions, and bam, they arrive at that lower bound.
That sounds pretty complex. Can you go into more detail about how they choose the points at each scale?
Of course. So at each scale, they focus on points within these cylinders around the diagonal.
Cylinders?
Yeah. They're big enough to contain points with high probability, but narrow enough to satisfy that constraint on path deviations.
So it's like a way to streamline the search for those promising points.
Exactly. And then within each cylinder, they randomly select a single point from the Poisson point process at that scale.
Combining geometric constraints with random sampling? Interesting.
Right. The size of those cylinders is crucial. It's determined by an optimization problem.
Okay.
Balancing the need to capture enough points, but also staying within the deviation constraint.
So carefully tuning those parameters to make this construction work.
Right. And by choosing them carefully, they guarantee with high probability they can build a path that captures a lot of weight at each scale.
While still following those constraints.
Exactly.
That's really cool. Combining those geometric and probabilistic arguments like that.
It's a powerful approach. It really shows how those combined perspectives can help us understand these complex systems.
So they construct this heavy path and get a lower bound for the passage time. Quite an achievement.
Indeed. It sets the stage for more research into this topic.
Now, before we move on, can you help me understand why we see those logarithmic corrections? Intuitively, I mean. Why doesn't the passage time just grow linearly with n?
That's a great question. It comes down to this tension you see between collecting those small rewards consistently and then targeting those large, less frequent ones strategically.
Okay.
For purely linear growth, the path would need to collect an average reward proportional to n over a distance of n.
Right.
But those occasional jackpots, they disrupt this average.
They mess up the neat linear pattern.
Exactly. The path might deviate from the direct route just to grab a jackpot, even if it misses some smaller rewards along the way.
It's like that risk-reward trade-off.
Precisely. And this constant balancing act between exploiting what's there and exploring for more leads to those logarithmic corrections in the growth.
Okay, that makes sense. It's amazing how such simple rules can lead to such complex behavior.
It is. This is what makes math so beautiful. It reveals those hidden patterns in the world around us.
So we might not know the exact growth rate yet, but we can still explore how the last passage time fluctuates around its mean.
Yes. That's where Theorem 2 comes in.
Okay, so moving from average behavior to understanding the spread, the possibility.
Yeah. Exactly. Theorem 2 states that even though we don't know the precise growth rate, the last passage time, it's actually concentrated around its mean.
In this heavy-tailed setting.
Yes. It doesn't vary wildly, despite all the randomness.
Oh, those jackpots don't completely throw off the predictability.
Right. The theorem gives an upper bound on the probability of large deviations from that mean.
Okay.
It states that the probability of the appropriately scaled last passage time deviating from its mean by more than, let's say, t, decreases faster than t to the power of negative 43.
So bigger deviation, less likely it is to happen.
Exactly.
It's impressive they can even quantify that.
It is. They use the Efron-Stein inequality, a powerful tool from probability theory, to bound the variance of a function of independent random variables.
Using a general tool for a specific problem. Nice. But if the last passage time is concentrated around its mean, does that mean the fluctuations are, like, negligible?
Another good question. Theorem 2 shows concentration, but the fluctuations aren't totally negligible.
Right.
Proposition 5.2 sheds light on this. It states that with a certain probability, though it decreases as n grows, the last passage time will still deviate from its mean by at least n.
So the fluctuations might not be as wild as in simpler cases, but they're not nothing either.
Precisely. And this connects to the transversal fluctuation of that best path, the geodesic, intuitively larger transversal fluctuations.
Yeah.
They generally lead to larger fluctuations in the last passage time, you see.
Makes sense. A path that deviates more, it has more chances to encounter those large values or to miss them.
Exactly. More freedom to move around, more potential for both gains and losses.
Gotcha. So what does Proposition 5.2 tell us about those transversal fluctuations in this case?
It suggests they're likely of order n divided by some power of log.
So the path still deviates, but maybe not as much as in other cases.
Right. It seems those logarithmic corrections are acting like, a stabilizing force.
Keeping things from getting too chaotic.
Precisely. It's fascinating how these subtle mathematical features can have such a big impact on the overall behavior.
Okay, that was a lot to absorb. We've looked at this heavy-tailed environment in detail.
Right.
Where do we go from here?
Now we switch gears to a different landscape.
Oh.
The branching random walk. This one brings in a new element. Correlated rewards.
Oh, okay.
Let's explore what challenges and insights it offers.
Sounds good. Lead the way.
So back to that city, rewards at every corner in the branching random walk, or BRW.
Okay.
The rewards in a neighborhood, well, they're influenced by the surrounding areas.
Right, like those clusters of affluent neighborhoods.
Sure. Yeah.
One wealthy block suggests nearby blocks are also well off.
Right.
We're dealing with correlated rewards now, not independent like in the heavy-tailed environment. How does this change things?
It brings new challenges, for sure.
Okay.
But also fascinating insights.
Right.
The paper, it adapts that multi-scale construction we talked about for the heavy-tailed case to analyze this BRW landscape.
Okay.
But instead of just focusing on those large individual rewards, the construction, it prioritizes paths that pass through regions with high concentrations of positive rewards.
So it's not just about hitting the jackpot, it's about consistently being in the right neighborhood.
You got it. But the challenge is, these good regions,
Yeah.
they emerge from this complex interplay of random variables at different scales.
Right.
They're not immediately obvious.
I see.
To capture this, the construction uses a tree of possible path trajectories.
A tree. Can you explain that a bit more?
Sure. Imagine a tree. Each level represents a different scale of the landscape.
Oh.
At the first level, we have a few initial paths. Each one explores a different part of the landscape.
Okay.
Then at the next level,
Yeah.
each of those paths, they branch out into multiple offshoots. Each one represents a possible refinement of the path at a smaller scale.
So it's like starting with a few main roads and then exploring different side streets and alleys along those roads.
Precisely. The construction, it evaluates the expected reward for each possible path segment.
Okay.
At each level, taking into account those correlations between rewards in that region, it's kind of like how we might assess the overall prosperity of a neighborhood.
Right.
Not just looking at the wealth of a single household.
Okay, so branching out possibilities, then evaluating them statistically based on those correlations.
Right.
But how do they choose which branches to keep exploring and which ones to prune?
That's where the correlated nature of the BRW comes in.
Okay.
Paths that are expected to lead to those regions, the ones with a higher concentration of positive rewards. They're favored.
Okay.
This is done by carefully analyzing the statistical properties of the BRW at each scale.
So statistical analysis guides the exploration.
Exactly.
You mentioned earlier that the scale separation, the difference between those levels in the tree,
Yeah.
it's not fixed.
Right.
How do they determine that?
That's a key difference from the heavy-tailed case.
Okay.
The scale separation, it's actually determined by an optimization problem.
Interesting.
It's carefully chosen to maximize the lower bound on the passage time.
So dynamically adjusting the zoom level to find the best route.
Exactly. Finding that optimal scale separation, it takes some intricate mathematical analysis.
I bet.
It depends on the specific characteristics of the branching random walk. Through this method, they establish Theorem 3, which provides a lower bound for that logarithmic correction exponent in the BRW.
Similar to Theorem 1, but specifically for the BRW.
Yes.
What does that lower bound look like?
Theorem 3 says the last passage time on the branching random walk, it grows at least as fast as n times the square root of log n.
Okay.
All divided by log of log n.
N times square root of log n divided by log of log n. That seems different from the heavy-tailed bound.
Good observation. The lower bound for the BRW, it's actually weaker than the one for the heavy-tailed environment with I equals 2.
Right.
Remember, that one was n times log n to the power of 34.
Yeah.
Divided by log of log n. Here, the exponent on that log n term, it's only 12.
So does that mean finding the best path in the BRW is easier than in the heavy-tailed case, I mean?
Well, not necessarily. These are just lower bounds. Remember, the actual growth rates that could be higher.
True.
But this difference, it suggests those long-range correlations in the BRW. They might make it harder to find a truly optimal path.
It's like the interconnectedness of those rewards, it's a double-edged sword.
Exactly. It creates regions of concentrated rewards, but it also restricts the path's flexibility in exploiting them.
I see.
Think of it like navigating a city with, well-defined economic zones.
Okay.
You might find a wealthy area, but moving between those zones, it could be restricted.
Right.
Hindering your ability to maximize your overall gain.
Okay, I get it. Those correlations add a whole new layer of complexity.
They do.
But even with those challenges, they still got a lower bound for the passage time.
Yes, and it's important to remember, even though it's weaker, it still shows the passage time grows superlinearly with n.
Okay.
This means that hierarchical structure, it has a significant impact.
In both scenarios.
Exactly. It's not just a simple average of rewards. There's a more complex dynamic happening.
Right. What about those fluctuations around the mean in the BRW? Do we see that same concentration behavior as in the heavy-tailed case?
That's where Theorem 4 comes in.
Okay.
And here we get even more precise information compared to that heavy-tailed scenario.
Interesting.
Theorem 4, it characterizes both the variance and the tail probabilities of the last passage time in the BRW.
So we're moving beyond just those lower bounds now.
Yes.
Getting a clearer picture of that variability.
Precisely.
What does Theorem 4 actually tell us?
It says the variance of the last passage time is proportional to n squared.
Okay.
And the probability of the appropriately scaled last passage time deviating from its mean by more than t, it decays as e to the power of n t squared.
So the variance, it tells us how spread out the distribution is.
Right.
And those tail probabilities, they tell us how likely we are to see big deviations.
Exactly.
Those are some precise statements.
They are. They tell us the fluctuations around that mean are of order n.
Okay.
And the chance of those large deviations, it decreases extremely rapidly as the deviation increases.
So even though the BRW is inherently random, that last passage time is still tightly controlled?
Precisely. This control, it comes from the structure of the BRW.
Okay.
Those correlations, while they make finding the optimal path tricky, they also impose a certain regularity on the system, preventing those wild fluctuations we saw in the heavy-tailed case.
It's fascinating how those correlations can both hinder and stabilize things.
It is. And this tight control, it also has implications for the transversal fluctuations of the geodesic in the BRW.
Okay.
Theorem 4 suggests the scale of these fluctuations, it's also of order n.
So the best path might wander a bit, but its deviations are still controlled.
Exactly. It's this delicate balance between exploration and constraint, shaped by those correlations in the BRW.
We've seen how the BRW brings unique challenges and insights,
Right.
leading to a very different but equally fascinating story compared to the heavy-tailed case.
It shows the richness of this research area,
Yeah.
different environments with their unique traits. They give rise to a variety of amazing phenomena.
Are there any other unexpected findings or twists in this research?
Actually, there's one more result.
Okay.
It might seem unrelated at first,
Gotcha.
but it connects back to the techniques we've been discussing.
Okay. It addresses a long-standing question in the field of last passage percolation, posed by James Martin.
All right.
It's about the growth of the last passage time in environments with independent, identically distributed rewards.
So we're stepping back from hierarchical environments now.
That's right. The question is,
Yeah.
can we have a weight distribution with a finite second moment, but where the last passage time grows superlinearly with n?
Finite second moment, meaning those rewards aren't too crazy, right?
Exactly. If they have a heavy tail, like the cases we've seen,
Yeah.
superlinear growth isn't surprising.
Right.
But what if the rewards are more well-behaved? Can the passage time still grow faster than linearly?
That's a really interesting question. So what's the answer?
Theorem 5 in this paper says no.
Wow, okay.
They prove that if the rewards are independent and identically distributed, with a finite second moment, the last passage time has to grow linearly with n.
So a finite second moment kind of tames the passage time. Precisely. And what's cool is they prove this by adapting those techniques from the multi-scale construction, the one for the heavy-tailed case.
Oh, wow.
They show that with a finite second moment, the path can't effectively exploit those occasional larger rewards to push the passage time beyond linear growth.
So the tools developed for one case, they unexpectedly shed light on a more general question.
It does. It shows how interconnected mathematical ideas are. Techniques for one problem can have implications in seemingly unrelated areas.
This deep dive has been quite a journey.
It has.
We've explored these hierarchical environments, uncovered hidden patterns,
Right.
tackled those complex constructions,
Yes.
and even touched on a broader question about the growth of passage times.
It's been a lot, but so interesting.
It really has. But it feels like we've only just scratched the surface.
Definitely.
What are some of the open questions
Oh, there are so many.
and exciting avenues for further research in this area?
Oh, tons. One of the biggest is figuring out those precise logarithmic corrections.
Okay.
For both the heavy-tailed and branching random walk models, we have the lower bounds.
Right.
But the exact form, those precise exponents,
Yeah.
there's still a mystery.
It's like we have some pieces of the puzzle, but we're missing that crucial one.
Exactly. Another fascinating direction is developing a complete fluctuation theory for these models.
Okay.
We have theorems 2 and 4.
Right. About the concentration.
Yes, but we need to go deeper.
I see.
Understanding those fluctuations, their distributions, and how they relate to the geometry of those geodesics, that's wide open.
So going beyond averages and bounds, trying to capture all the possibilities.
Precisely. And this ties into universality. We talked about KPZ universality.
Yeah.
But can we make a similar framework for these hierarchical environments?
Interesting.
Do these models have entirely new universality classes, distinct from KPZ?
Big questions.
Right. Deep connections to statistical physics.
It's like we're exploring this landscape of randomness and structure, searching for those universal laws that govern these complex systems.
Absolutely. And speaking of new territory, a natural next step is to explore last passage percolation,
Okay.
but on even more complex landscapes.
Like what?
Like the Gaussian free field.
Oh, wow.
It has those logarithmic correlations like the BRW,
Okay.
but with an even more intricate structure.
So the Gaussian free field, that's the ultimate test.
You could say that. Analyzing LPP on that would be a huge breakthrough.
What would it tell us?
It could reveal some deep connections between probability, geometry, statistical physics.
It's amazing how these abstract mathematical concepts can have such real-world implications.
It is remarkable. And that's what makes this field so exciting.
Definitely.
So many unanswered questions.
Yeah.
Mysteries waiting to be solved.
Well, this deep dive has been incredible.
Yeah.
We've explored these fascinating environments, uncovered those hidden patterns,
Right.
tackled complex math, even got a glimpse of the broader world of last passage percolation.
A great journey.
It really has.
It shows the power of human curiosity, our drive to understand the world.
To our listener out there, if you're intrigued by randomness and structure,
Yes.
the challenge of finding order in chaos, dive into last passage percolation.
You might make some groundbreaking discoveries yourself.
There's a whole universe of mathematical beauty out there.
Happy exploring.
Welcome to the Deep Dive. Today, we're going on a journey exploring the fascinating world of last passage percolation in hierarchical environments.
Buckle up, because we're about to unpack a recent research paper titled Last Passage Percolation in Hierarchical Environments by Ganguly, Ginsburg, and Nam.
Wow. What's so captivating about this paper is its focus on environments with inherent structure that repeats across different scales.
Exactly.
It's like exploring a landscape where instead of rolling hills, you encounter repeating patterns of towering mountains with their own intricate peaks and valleys.
Yes, like those Russian nesting dolls.
Oh, okay, yeah.
But with a fascinating blend of randomness at each level.
Before we journey further, can you give us a quick breakdown of last passage percolation, or LPP, for our mathematically inclined audience?
In essence, LPP involves finding the path through a grid, moving only up or right, that maximizes the total collected weight, where each point on the grid is assigned a random weight. This optimal path is often referred to as the geodesic.
So imagine navigating a city grid with random traffic conditions at each intersection.
Exactly.
LPP is about finding the route that minimizes your travel time despite those unpredictable delays.
Precisely.
Now, the environments explored in this paper aren't just any random grids.
Right.
They have a built-in hierarchical structure. This means that similar patterns of randomness appear as you zoom in or out.
Exactly.
Like discovering fractals within the randomness itself.
Like fractals, yes.
Okay, I'm starting to see why this is so intriguing. How does this hierarchical structure affect the usual predictions about LPP? Does it disrupt the expected hat?
It certainly does. Normally, with well-behaved random weights, LPP falls under the Cardar-Parisi-Zhang KPZ universality class. This means the fluctuations in the last passage time and the geodesic's wiggliness follow specific patterns predicted by the KPZ equation. These patterns are characterized by scaling exponents for the passage time fluctuations and as for the transversal fluctuations of the geodesic with the KPZ relation =1.
Right, the KPZ universality class. But I'm guessing this hierarchical structure throws a wrench into those predictions.
Precisely. When long-range correlations exist in the weights, those KPZ predictions might not hold. Imagine hidden dependencies between those traffic conditions in our city analogy. Rush hour in one district might affect traffic flow in another miles away.
Fascinating. So how does this paper explore LPP in these complex hierarchical scenarios?
This paper delves into two specific environments. The first involves independent weights, but with a heavy-tailed distribution. Think of a landscape dominated by occasional extremely large mountains. The second is based on the branching random walk, or BRW, a model that generates randomness with an inherent hierarchical structure, much like a Gaussian free field, but with a beautiful tree-like organization.
Heavy-tailed distributions and BRW.
Got it.
Let's dive into the paper itself. In the introduction, they lay the groundwork for their exploration, defining key concepts and setting the stage for their findings. They start by defining last passage percolation on the lattice Z, where each vertex V has a random weight xV. The last passage time, denoted as Ln, is the maximum sum of weights along any upright path from 0, 0 to n.
Yes. They emphasize that this definition can be generalized to find the last passage time between any 2 points on the lattice, not just 0, 0, and n. This introduces the notion of a random metric structure induced by LPP.
Interesting. They then move on to discussing the KPZ universality class and its relevance to LPP.
Right. They point out that when the random weights are light-tailed and their correlations decay rapidly, the fluctuations in the last passage time, Ln, are expected to scale like n13, and the maximum deviation of the geodesic from the diagonal scales like n23. These scaling exponents are characteristic of the KPZ universality class, named after the physicists Cardar, Parisi, and Zhang, who studied these types of random growth models.
So under these nice conditions, LPP behaves in a predictable way. But I suspect the paper then highlights how this predictability breaks down in hierarchical environments.
Exactly. The presence of long-range correlations in such environments disrupts the typical KPZ behavior, making accurate predictions about the last passage time and geodesic fluctuations much more challenging.
The paper then focuses on the case of heavy-tailed weights with a power law tail decay, where the probability of a weight xv exceeding a value 2 decays like t as that goes to infinity.
Yes, they introduced the Flory heuristic, a method used to predict scaling exponents in this heavy-tailed regime. It suggests that the geodesic, while aiming for maximum weight, will typically stay within a certain distance of the diagonal, where the largest weights are most likely to be found.
It's like finding the optimal balance between exploring for those massive weight mountains and sticking to a more direct route to avoid losing too much ground.
Precisely. The Flory heuristic suggests that if the maximum geodesic deviation is of order nuck, the geodesic would typically be confined within a region around the diagonal with a volume proportional to n1 plus x. The largest weight within this region would be roughly of order n1 plus x, giving us Rnux 1 plus x.
So we have a relationship between the fluctuation exponent and the geodesic deviation exponent based on the tail exponent.
Right. But deviating from the diagonal also comes at a cost. Due to the concave nature of the limit shape, this cost is of the order of n to 1. The Flory heuristic balances these two contributions, leading to the equation 1 plus x for 1. Solving this alongside 1 plus x here, we get n tilde 1 plus equal 1 and n tilde 1 plus equal to 1.
Interesting. So by considering this trade-off between exploration and efficiency, the Flory heuristic provides predictions for the scaling exponents.
Yes, and the authors point out that these predictions, while heuristic, have been supported by numerical evidence and are believed to hold for 8 to 5. However, rigorous mathematical analysis in this regime remains an open problem. They also highlight that for the TELA 5, these predicted exponents differ from the KPZ values, suggesting that each value of A in this range corresponds to a distinct universality class.
So we have different behaviors for LPP depending on the tail exponent. What happens when A is less than or equal to 2?
For 0 to 2, the largest weights dominate both the fluctuations and the leading order of the last passage time, leading to exponents 2 in Forticores and verse 1. This regime, characterized by the overwhelming influence of the largest weights, has been rigorously analyzed by Hambly and Martin in 2007.
Okay, so different values of I lead to different regimes of behavior. The paper then highlights the transition points at IR2 and i.i.d. worth 5,
Right.
calling them critical points.
These critical points are where the model exhibits fascinating behaviors like scale invariance and fractal behavior. Think of those intricate coastlines where similar patterns appear as you zoom in or out. These behaviors often introduce logarithmic correction terms in quantities like the last passage time, adding another layer of complexity.
So those critical points are where things get really interesting, but also much harder to analyze.
Precisely.
I can only imagine. The authors then point out the limitations of existing methods like the Flory heuristic, which are primarily effective for analyzing leading order polynomial behavior, but fail to capture those delicate logarithmic corrections at the critical points.
That's where this paper steps in, introducing a new framework for studying LPP in hierarchical environments, particularly focusing on those critical cases where traditional methods fall short. Their framework is based on a multi-scale analysis approach, carefully dissecting the problem at different levels of detail to uncover hidden structures and obtain more precise bounds.
Multi-scale analysis. Very interesting. They then dive into two specific examples: the I equals 2 heavy-tailed model and the branching random walk. Before we explore their results, let's clarify what they mean by hierarchical environments, as described in section 1.0.1.
In essence, hierarchical environments exhibit a multi-scale structure where the randomness looks similar at different levels of detail. Imagine zooming in on a coastline and seeing similar patterns of inlets and bays repeated at smaller and smaller scales. This concept is central to their analysis.
That's a helpful analogy.
Yeah.
So in the context of LPP, how does this idea of hierarchical randomness manifest itself?
A good illustration is provided in the paper using the A2 heavy-tailed model. If you divide the square grid from 0, 0, to n into smaller squares of size 2k by 2k, the largest weight within each smaller square would typically be on the order of k due to the heavy-tailed nature of the distribution. So, as k increases, the largest weights get smaller, but they remain dominant features within their respective scales.
It's like a hierarchy of mountains, with massive peaks spread out across the landscape, and within each mountain range, you find smaller but still significant peaks.
Precisely. The paper suggests that this entire landscape can be envisioned as a superposition of Poisson point processes, one for each scale hay, describing the locations of the largest weights at that particular scale.
Poisson point processes, I see. So each scale of randomness is represented by its own Poisson point process.
Yes, and this idea of representing different scales of randomness using Poisson point processes is a crucial tool in their analysis. They employ a similar approach when discussing the branching random walk, the second hierarchical environment they focus on.
Let's talk about the branching random walk, or BRW then. How does it fit into this picture of hierarchical environments?
The BRW is a classic example of a hierarchical model. Imagine a family tree where each node represents a random value, and the values at different levels of the tree are correlated. This structure can be visualized as a tree, with each level corresponding to a different scale. At the coarsest level, you have a single random value. As you move down the tree, this value branches into multiple values, each representing a finer scale.
Like those Russian nesting dolls again. But now each doll contains smaller dolls with correlated features.
Precisely. The paper points out that the BRW can be viewed as a coarse approximation of the two-dimensional Gaussian free field, or GFF.
The Gaussian free field. It's familiar, but could you refresh our memory?
The GFF is a random function on a two-dimensional space. Its values at different points are correlated, and the strength of this correlation decays logarithmically with distance.
So the correlation fades slowly as points get farther apart.
Exactly. And this slow decay of correlation gives the GFF, and by extension the BRW, its intriguing multi-scale properties.
Okay, I'm starting to grasp how the BRW exemplifies a hierarchical model with correlated randomness. How do the researchers use this model to investigate LPP?
They define an LPP model on the BRW, where each grid point's weight is determined by the corresponding BRW value. They then leverage the BRW's hierarchical structure to analyze the last passage time and geodesic behavior within this model.
This is getting deep. I'm eager to see their findings.
But before revealing their discoveries, it's worth highlighting the limitations of current techniques for studying LPP in these intricate hierarchical environments. As we discussed earlier, the Flory heuristic, while effective for leading order behavior, struggles to capture those subtle logarithmic corrections at critical points. Even sophisticated simulations face difficulties in accurately resolving those corrections at the scales needed for reliable predictions.
It seems new approaches are needed for tackling these challenges.
That's precisely what this paper aims to provide. They develop a multi-scale analysis framework to obtain bounds on those critical exponents and prove near-optimal concentration results for both the heavy-tailed and BRW models.
Multi-scale analysis, that's their secret weapon. Can you elaborate on its application in this context?
In simple terms, it involves dissecting the system at various levels of detail. Think of zooming in and out of a map. For LPP, it entails constructing paths piece by piece, considering different scales of randomness at each step. They carefully choose weights for their paths based on both magnitude and position relative to the diagonal. Like navigating a city considering not just traffic, but also landmarks and pedestrian patterns at different levels of detail.
That sounds like a delicate balancing act.
It certainly is. They have to cleverly account for the correlations between weights at different scales, especially in the BRW case. In section 1.1, they outline their findings, starting with the i.i.d 2 heavy-tailed model.
Why is i.i.d so significant?
It represents a critical point where the model's behavior changes drastically. For ek2, the limit shape exists, but for ek2, it becomes infinite.
That makes sense. What did they discover about the ek2 case?
Their first major result, presented in Theorem 1, establishes a lower bound on the last passage time growth rate. They prove that with high probability, ln is at least of order n log n, 34 log n. This indicates that even though the limit shape is infinite for ek2, the last passage time still grows in a controlled way, albeit with a logarithmic correction factor, a signature of the critical behavior at lek2.
So, despite the infinitely rough landscape, there's a minimum speed limit for traversal.
Precisely. They then present a concentration result in Theorem 2, showing that the last passage time fluctuations around its average are relatively small, which is surprising considering the presence of those heavy tails.
You'd expect those massive weights to cause more erratic fluctuations.
Indeed, but their analysis demonstrates a balance between the extreme values and the other weights.
Fascinating. They then move on to the BRW model. What did they uncover there?
Similar to the heavy-tailed case, Theorem 3 establishes a lower bound on the last passage time growth rate for the BRW model. However, this bound is slightly weaker, at least of order n, log n, 12 log n, with high probability, likely due to the long-range correlations restricting path choices compared to the independent heavy-tailed case.
It's like navigating a city where traffic conditions are interconnected across different districts, limiting your route options compared to a city with independent random traffic at each intersection.
Precisely. And in Theorem 4, they achieve something remarkable. They not only prove concentration, but also obtain matching upper and lower bounds on the variance of the last passage time. They show that the variance is of order n2, implying that the fluctuations around the average are of order n.
Matching upper and lower bounds. Very impressive.
It indeed highlights the effectiveness of their multi-scale analysis.
Okay, we've discussed growth rates and concentration. Now for that intriguing limit shape question where they debunked a long-standing belief.
That's covered in section 1.1.2, where they address which weight distributions ensure a finite limit shape. They summarize the existing literature, starting with early results from the 1990s, like Glynn and Witt's work showing that exponential tail distributions lead to a finite limit shape. They also mention subsequent work by Cox, Gandolfi, Griffin, and Keston, who established a weaker sufficient condition involving a stronger moment condition.
So researchers have been searching for the most general conditions for finite limit shapes. What's the current state of the art in this area?
The most significant breakthrough came from James Martin in the early 2000s. He showed that if a specific integral involving the distribution's tail probability is finite, then the limit shape is guaranteed to be finite.
So that integral acts as a test for a well-behaved distribution leading to a finite limit shape.
Exactly. And what's remarkable is that Martin's condition is very close to simply requiring a finite second moment, a measure of the distribution's spread.
So it seemed like a finite second moment was almost enough to guarantee a finite limit shape.
That was the prevailing intuition. But this paper shatters that notion. In Theorem 5, they construct a weight distribution with a finite second moment, but a superlinear last passage time growth, implying an infinite limit shape.
A significant discovery. How did they manage to achieve this?
They utilized their multi-scale analysis, crafting a distribution that barely has a finite second moment. They then leveraged the fact that their lower bound in Theorem 1 has an exponent of 34, which is strictly greater than 12. This difference is crucial for their construction to work.
That's impressive. They used their insights from the heavy-tailed case to debunk a long-standing conjecture. Now, after all this discussion of results, the paper finally reveals how they prove them, right?
Yes. In Section 2, Proof Ideas, they outline their strategies, highlighting key techniques and insights. They begin by discussing the straightforward upper bound for the last passage time, particularly in the HE2 heavy-tailed case. They show that the last passage time can be decomposed into contributions from different scales, each represented by a Poisson point process, essentially breaking down the landscape into those hierarchical levels of mountains and peaks.
They're essentially analyzing the landscape at different resolutions, focusing on those dominant features at each scale.
Precisely. By analyzing each scale's contribution and employing concentration inequalities for Poisson processes, they establish an upper bound of order n log n for the last passage time with high probability.
Okay, that's the upper bound. What about their main contribution, the lower bound?
That's where their multi-scale analysis shines. They explain their strategy for constructing a path that achieves a large last passage time. They build this path piece by piece, focusing on different scales of randomness at each step.
It's like finding that optimal route through the city, considering not just traffic, but also road layout, landmarks, and even pedestrian patterns at different levels of detail.
A great analogy. They have to be strategic about which weights to include in their path, carefully balancing contributions from different scales to obtain the best lower bound.
This multi-scale construction sounds intricate. How does it actually work?
They begin by considering a simplified scenario with just two consecutive scales of randomness, represented by Poisson point processes O min to us. Think of O as describing the largest weights and us as describing the next largest weights. The goal is to construct a path that collects many points from both O and us, while adhering to the upright movement constraint of LPP.
So it's about finding a route that hits major attractions and some interesting smaller spots along the way.
Exactly. But there's a catch. If the path focuses too much on collecting points from O, it might have to zigzag a lot, missing out on potentially valuable points from us.
So it's a trade-off between exploration and efficiency.
Precisely. To strike the right balance, they introduce the concept of slopes. Imagine connecting consecutive points on the path with straight lines. The slope of each segment indicates how much the path deviates from the diagonal.
Right. The slopes tell us how much the path is wiggling around.
They recognize that if the slopes are close to 1, meaning the path stays relatively parallel to the diagonal, they can collect a good number of points from both O and TO without excessive zigzagging.
Okay, but how do they control those slopes?
That's where the multi-scale nature of their construction shines. They divide the grid into smaller squares or cylinders of a carefully chosen size. They then ensure that the path stays within a certain distance of the diagonal within each cylinder.
Those cylinders act as guardrails, preventing the path from straying too far.
Exactly. By carefully choosing the cylinder size and the allowed deviation within each, they maintain the slopes within a specific range, allowing for efficient collection of points from both O and toe.
That's clever. But it sounds delicate. They must be precise with their calculations.
Indeed, they go through those details meticulously in the paper. They also highlight a key insight that significantly improves their lower bound, exploiting cancellations between the slopes of different line segments along the path.
Can you elaborate on these cancellations?
Imagine two consecutive line segments with slightly different slopes. If one slope is slightly above one and the other slightly below one, their overall deviation from the diagonal might be smaller than if both were either above or below one.
So the slopes can partially compensate for each other, allowing the path to stay closer to the diagonal overall.
Precisely. By accounting for these cancellations, they improve their lower bound. They then analyze the contributions from different scales using concentration inequalities and Poisson point process arguments to demonstrate that with high probability, their constructed path achieves the desired lower bound on the last passage time.
Amazing. It's fascinating how they combine geometrical and probabilistic arguments to construct this high-weight path. What about the BRW case? How does their approach work there?
The general strategy remains similar, but the details become more intricate due to the BRW's long-range correlations. Remember the family tree analogy. The hierarchical structure introduces dependencies between weights at different scales, making it trickier to construct a path that collects a lot of weight.
It's like those city traffic patterns influenced by region-wide events. You can't simply hop between streets hoping for a clear path.
Exactly. To navigate this correlated landscape, the path can't just jump around collecting large weights, as in the heavy-tailed case. Instead, it must spend considerable time within specific boxes, benefiting from shared high values. Think of exploring a neighborhood with many great restaurants. It's worth covering the entire area, not just bouncing between random spots.
That makes sense. How do they adapt their construction to this scenario?
They still employ a multi-scale approach, but instead of cylinders, they utilize a tree-like structure to explore possible path trajectories within each scale. Their construction prioritizes maximizing weight within each box, exploiting shared randomness. However, to sample from diverse independent Gaussian values, they loosen control over the path's slope compared to the heavy-tailed case.
So they sacrifice some control over the path's wiggliness to tap into those correlated high values.
Precisely. This compromise is reflected in their slightly weaker lower bound for the BRW model compared to the heavy-tailed case. Choosing the scale separation also becomes crucial, requiring optimization to balance leveraging correlations with ensuring sufficient path options.
It sounds like their approach for the BRW model blends their heavy-tailed strategy with new techniques specifically designed to address those long-range correlations.
Exactly. And their success improving concentration and fluctuation results for the BRW, despite these added challenges, really showcases the power and flexibility of their multi-scale analysis framework.
Welcome back to the deep dive. In the last part, we laid the groundwork for understanding last passage percolation in hierarchical environments, diving into the intricacies of heavy-tailed distributions and the branching random walk model. Now it's time to roll up our sleeves and get into the nitty-gritty of the researcher's multi-scale construction.
Indeed. Let's delve into Section 3, Preliminaries, where they lay the foundation for their mathematical arguments. They start by clarifying notation, including how they'll be handling constants, those ever-present C's and C's in proofs. More importantly, they define their geometric language for discussing rectangles, slopes, and those intriguing cylinders within this two-dimensional grid context.
I'm still picturing those cylinders as long, tube-like structures. Are we constructing rockets in this mathematical landscape?
Not quite rockets, but the analogy isn't that far off. Imagine narrow strips surrounding the main diagonal of the grid. Those are their cylinders. It's as if they're saying, our path has some freedom to meander, but it can't stray too far from the central line. These cylinders help them quantify the path's deviation, which is crucial for their analysis.
So the cylinders act as boundaries, ensuring the path doesn't wander off on unproductive tangents.
Exactly. Exploration is encouraged, but it needs to be strategic. In this section, they connect the number of lattice points, those discrete points on the grid, within a cylinder to the cylinder's area. It's a subtle but powerful connection.
Why is that connection significant? Seems like a minor detail.
It's subtle but crucial. By relating these two quantities, they simplify their arguments. Instead of meticulously counting individual grid points, they can work with areas, a smoother and more elegant approach. They even utilize Pick's theorem, A beautiful result connecting geometry and number theory to formalize this connection.
I always appreciate those unexpected links between seemingly disparate areas of math. It highlights the interconnectedness of mathematical ideas.
Indeed. This lemma connecting grid point counts and areas will be a valuable tool in their later proofs. They also introduce another handy lemma in this section: the worst-case slope bounds. Remember those line segments connecting the path's points and their slopes, which indicate the path's wiggliness?
Yes, those slopes that tell us how much the path is deviating from the diagonal.
This lemma provides a way to control how much the slopes of nearby segments can differ. Imagine two cylinders, one slightly ahead of the other along the diagonal. This lemma essentially says the slope of the line connecting a point in one cylinder to a point in the other can't be too extreme. It sets limits on how abruptly the path can change direction.
So it's like ensuring the path doesn't make any sharp U-turns, instead transitioning smoothly between cylinders.
Precisely. These slope change bounds are crucial when constructing the path scale by scale. With these preliminaries established, let's move to the heart of their analysis. Section 4, critical heavy-tailed last passage percolation, where they tackle their first example.
Time to confront those massive mountains in our heavy-tailed landscape.
Exactly. They begin by defining scales, a concept we touched upon earlier. Remember breaking down the grid into smaller squares of size 2K by 2K. They assign a scale to each vertex based on its weight's magnitude. The largest weights are at scale 0, the next largest at scale 1, and so on.
So scales act as a ranking system for the weights. Higher scale, smaller weight.
Precisely. They're particularly interested in scales separated by multiples of a specific value, denoted as which they set as 100 log log n.
100 log n. Another one of those strangely specific logarithmically flavored parameters? There must be a reason for this peculiar choice.
This specific value of BEB balances two competing needs. They want enough scales to capture the problem's hierarchical structure while ensuring that each scale's randomness is well behaved enough to allow for good concentration properties.
Concentration yet again. It seems like a recurring theme in their analysis.
It's a powerful tool in probability, especially in settings with high randomness. It ensures their estimates are robust against wild fluctuations. Choosing carefully is akin to setting the right resolution for their analysis.
Too coarse a resolution, and they miss crucial details. Too fine, and the noise obscures the signal.
Exactly. They're aiming for a Goldilocks resolution, zoomed in enough to see the structure without getting lost in the randomness. Having defined scales, they present a key proposition outlining their multi-scale construction.
That's their core strategy, building paths with high weight, piece by piece, focusing on different scales at each step.
Precisely. This proposition provides the blueprint. They claim they can construct a sequence of vertex sets, V1, V2, up to Vm, where m is another carefully chosen value, log n. These V-sets will contain the vertices forming their High-Wide path.
So they're not just picking random vertices, they're ensuring they can be connected into a valid path.
Right. Their second claim concerns scales. They assert that for each log, the set V1 consists entirely of vertices of scale odd. In simpler terms, they're constructing the path scale by scale, adding vertices from progressively smaller scales.
Like building a pyramid, starting with the largest blocks at the bottom and adding progressively smaller ones as you go up.
An excellent analogy. Their final and perhaps most crucial claim is that with high probability, the number of vertices in each set V1 is at least of order 2, where n is another carefully chosen parameter.
So they're not just building any path, they're ensuring it contains a significant number of vertices from each scale, allowing them to collect substantial weight from those different levels of mountains and peaks.
Precisely. This deliberate construction, rigorously proven using probabilistic and geometric arguments, sets them up to achieve those impressive results about the last passage time and its concentration.
It's like watching a master architect meticulously planning every detail to achieve both structural integrity and aesthetic beauty.
Indeed. In section 4.1, they elaborate on their multi-scale construction. Recall that it's an inductive process, building up layer by layer. Their base case is simple. A set VO containing just the starting and ending points of our grid, 0, 0, and n. Then they demonstrate how, given V at some level, they can construct the next level, V plus 1.
So assuming they've laid the first few layers of blocks, how do they add the next one?
This is where their geometric prowess comes into play. Imagine connecting consecutive points in V with straight lines, forming rectangles across the grid.
Those rectangles sound familiar. Are these related to the cylinders we discussed earlier?
You're spot on. Within each of these rectangles, they focus on even smaller rectangles aligned along the diagonal. Then, within these smaller rectangles, they search for vertices of scale, +1, residing within carefully chosen cylinders.
Wait, rectangles within rectangles and cylinders within those. This is getting intricate.
It is, but bear with me. By carefully choosing these cylinders, they control the slopes of the line segments connecting the new vertices they're adding. Remember that lemma about worst-case slope bounds? That comes into play here, ensuring the path avoids drastic turns.
Right. Those bounds prevent the path from going on wild detours. So they're saying, we'll add vertices from scale +1, but only if they lie within these specific cylinders, guaranteeing nice slope behavior.
Precisely. The cylinders they choose are those labeled scalar 2j + 1, where I is another carefully chosen parameter, log n.
Log n. Another one of those curiously specific logarithm-infused parameters. These researchers seem to have a fondness for logarithms.
Their affection for logarithms is well placed. This choice of gra balances the need for good concentration properties with the desire to allow sufficient flexibility in the path construction.
Another example of their careful balancing act.
Exactly. Once they've identified the cylinders containing vertices of scale, +1, they select one vertex from each cylinder and add it to their growing set, V +1. This process is repeated for each rectangle, adding vertices scale by scale, cylinder by cylinder, until they've constructed the entire set V +1.
It's like a beautifully choreographed dance, each new dancer added to the stage in a way that maintains the performance's overall harmony.
A beautiful analogy. This meticulous construction is what allows them to prove those remarkable results about the last passage time and its concentration.
Okay, they've outlined their construction blueprint. Now, do they dive into proving it actually works?
Indeed they do. In section 4.2, they deduce several key properties of their vertex sets, crucial for proving their main results. They begin by proving parts 1 and 2 of proposition 4.2, which confirm that their construction yields a valid path and that it's built scale by scale.
Those are the foundational pieces, verifying that their blueprint translates into a structurally sound path.
Precisely. They achieve this through careful geometric analysis, utilizing their definitions of rectangles and cylinders. They leverage the fact that their construction ensures consecutive vertices are well separated and the connecting line segments have controlled slopes due to their careful choice of cylinders.
So those geometric constraints help tame the randomness of the weights, ensuring the path stays on track. But I'm sure there's more to it than just verifying the path structure.
You're right. They go further by proving a lemma that establishes a priori bounds on the areas and slopes of the rectangles formed by consecutive vertices at each scale.
A priori bounds. So they're setting limits on those rectangles' stretch and tilt even before knowing the vertices' exact locations.
Exactly. It's like setting safety regulations during construction to prevent the structure from becoming unwieldy or collapsing. These bounds are crucial for maintaining control and preventing chaos in the path construction. They leverage their earlier results on scales and cylinders to establish these bounds.
It's impressive how they build this logical edifice brick by brick, lemma by lemma, leading to their main results.
It showcases the power of rigorous mathematical analysis. Now, in section 4.3, they tackle the most challenging aspect, proving part 3 of proposition 4.2, which asserts their vertex sets are large enough to achieve a high last passage time.
Right. That's the part guaranteeing the path collects substantial weight from those different scales of mountains and peaks. This is where the abstract construction meets the concrete goal of maximizing weight.
Exactly. To prove this, they dive deep into the problem's probabilistic structure, utilizing concentration inequalities and clever arguments involving Poisson point processes.
This paper is truly multifaceted, blending geometry, probability, and analysis.
It's a beautiful demonstration of how different mathematical disciplines can synergize to solve complex problems. A key insight here is exploiting the cancellations between the slopes of rectangles at different scales. Recall how those slopes can partially compensate for each other, allowing the path to stay closer to the diagonal?
Yes, that was a clever trick. Essentially, they can allow slightly larger deviations at individual scales as long as they eventually cancel out, keeping the path on track.
Precisely. To formalize this, they prove a crucial lemma about slope cancellations. If the slopes of consecutive rectangles meet certain conditions, the overall contribution to the last passage time is greater than what a naive approach ignoring these cancellations would yield.
So they're squeezing out every bit of performance from their path construction, using those subtle cancellations to boost their lower bound.
Exactly. This insight allows them to push their bound further. They then analyze the contributions from different scales, using concentration inequalities and Poisson point process arguments to show that, with high probability, their vertex sets have enough points to achieve the desired lower bound on the last passage time.
This analysis is incredibly detailed. They're leaving no stone unturned.
Their thoroughness is commendable. Now, having tackled the heavy-tailed case, how about those long-range correlations in the branching random walk model? How do they adapt their approach?
That's what I'm eager to find out. BRW seems like a whole different beast.
It does present unique challenges. Remember that in the heavy-tailed model, each vertex's weight is independent. But in the BRW, weights within a box share the same Gaussian value, creating those long-range correlations.
It's like navigating a city where traffic patterns are interconnected across entire districts, not just random at each intersection.
Precisely. This interconnectedness means a path can't simply jump around collecting large weights like it could in the heavy-tailed case. To accumulate a large passage time in the BRW, a path needs to spend considerable time within specific boxes, taking advantage of those shared high values. Think of exploring a neighborhood with many great restaurants. It might be worth covering the entire area, not just bouncing between a few random spots.
Makes sense. So how do they modify their construction for this scenario?
They, again, employ a multi-scale construction, but instead of cylinders, they utilize a tree-like structure to explore potential path trajectories within each scale. Their construction prioritizes maximizing weight within each box, exploiting those shared random values. However, to sample from diverse, independent Gaussian values, they have to sacrifice some control over the path slope compared to the heavy-tailed case.
So they trade some control over the path's wiggliness to access those correlated high values. It's a strategic compromise, like sacrificing some speed for stability.
Exactly. This trade-off is reflected in their slightly weaker lower bound for the BRW model compared to the heavy-tailed one. The choice of scale separation also becomes crucial here, requiring optimization to strike the right balance between leveraging correlations and ensuring enough path options.
It sounds like they've combined elements of their heavy-tailed strategy with new techniques tailored to those persistent long-range correlations.
That's right. And their success improving concentration and fluctuation results for the BRW, despite these complexities, truly highlights their multi-scale analysis framework's power and adaptability.
Welcome back to the deep dive. We've spent the last two parts exploring the fascinating world of last passage percolation in hierarchical environments, dissecting those challenges posed by heavy-tailed distributions and the branching random walk model. Now let's turn our attention to the specifics of their analysis for the BRW model as outlined in Section 6.
Right, in Section 6, titled Branching Random Walk, the authors present their findings for the BRW model, highlighting both the parallels and the key distinctions from the heavy-tailed environment. They begin by reminding us that in the heavy-tailed model, each vertex has an independent weight. However, in the BRW, all weights within a specific box share the same Gaussian value, creating those long-range correlations that make this model particularly challenging.
It's like realizing that traffic congestion isn't just random. It's influenced by broader patterns like rush hour or major events affecting entire regions of the city. You can't simply hop between streets hoping for a clear path.
Precisely. This interconnectedness in the BRW means that a path can't just jump around collecting large weights as it could in the heavy-tailed model. To achieve a substantial last passage time in the BRW, a path needs to spend significant time within certain boxes, capitalizing on those shared high values. It's akin to realizing that if you're in a neighborhood renowned for its culinary scene, it might be worth exploring the entire area rather than just bouncing between a few random restaurants.
Makes sense. So how do they adapt their multi-scale construction to this more intricate, correlated landscape?
They still utilize a multi-scale approach, but as we mentioned earlier, they have to adapt their strategy to handle those long-range correlations. Instead of those cylinders we discussed in the heavy-tailed case, they employ a tree-like structure to explore potential path trajectories within each scale. Their construction focuses on selecting paths that maximize the total weight collected within each box, taking advantage of that shared randomness. However, to ensure their path samples from a variety of independent Gaussian values, they need to relax their control over the path slope compared to the heavy-tailed case.
So they're essentially trading some control over the path's wiggliness for the opportunity to capitalize on those correlated high values. It's a strategic trade-off, like sacrificing a bit of speed for increased stability.
Exactly. And this trade-off is reflected in their slightly weaker lower bound for the BRW model compared to the heavy-tailed one. The choice of scale separation, that parameter we've discussed, also becomes crucial here, requiring an optimization process to find the ideal balance between leveraging correlations and ensuring sufficient path options.
Okay, let's delve into the specifics of their BRW construction. Starting with the definition of the BRW itself, how do they formally set up this hierarchical structure?
They start by defining the BRW on a binary tree, which you can visualize as a structure where each node branches into two child nodes. They consider a sequence of independent, standard Gaussian random variables associated with each edge of this tree. Each vertex's value is then defined as the sum of the Gaussian variables along the path from the root of the tree to that vertex. This recursive definition beautifully captures the idea of hierarchical correlated randomness.
So the randomness at a particular vertex is influenced by the randomness of all its ancestors in the tree. It's like inheriting traits from your parents, grandparents, and so on, with each generation adding its own random twist.
Exactly. And this hierarchical structure of the BRW is what makes it so well suited for modeling those long-range correlations we've been discussing.
Now, how do they connect this abstract BRW on a tree to the concrete setting of LPP on a two-dimensional grid?
That's where their embedding comes in. They embed this binary tree into the two-dimensional grid in a way that preserves the hierarchical structure. Each vertex of the tree is mapped to a specific box in the grid, and all vertices within that box inherit the same Gaussian value from their corresponding tree node.
It's like assigning a family name to each box in the grid, and everyone within that box shares the same family history, represented by that Gaussian value.
That's a great way to put it. And this embedding is what allows them to transfer the BRW's hierarchical correlations onto the grid, creating a challenging landscape for LPP.
Okay, I see how they've set up this intricate BRW model. Now, how do they actually construct a path that achieves a high last passage time in this challenging setting?
They again employ a multi-scale approach. But as we mentioned earlier, they have to adapt their strategy to handle those long-range correlations. Instead of those cylinders we used in the heavy-tailed case, they utilize a tree-like structure to explore potential path trajectories within each scale. Their construction prioritizes maximizing the total weight collected within each box, capitalizing on those shared Gaussian values.
So they're still building paths piece by piece, but now they're working with boxes instead of cylinders.
Precisely. And within each box, they aim to select the path that accumulates the most weight, given the shared Gaussian value assigned to that box. They think of this path selection process as traversing a smaller tree within each box, where each level of the tree represents a finer scale of resolution.
It's like zooming in on a map, then zooming in further within a particular region to find the best route through that smaller area.
Exactly. And this hierarchical path selection process within each box is key to their approach. They're essentially exploiting the BRW's hierarchical structure to guide their path construction.
But don't they need to ensure their path samples from a diverse set of independent Gaussian values? If they just stay within a single box, wouldn't they be limited by that single Gaussian value?
You're right. To avoid getting stuck in regions with low Gaussian values, they need to ensure their path explores different boxes at each scale. They do this by carefully selecting a set of well-separated boxes at each scale, ensuring that the Gaussian values associated with those boxes are independent.
So it's like ensuring your city tour doesn't just stay within a single neighborhood, but also explores different districts with their unique characteristics.
Precisely. And this careful box selection process is crucial for their analysis. They need to strike a balance between exploiting the correlations within each box and exploring enough independent boxes to ensure their path has the potential to collect a substantial amount of weight.
This sounds incredibly intricate. How do they formalize this box selection process and prove that their path construction actually achieves a high last passage time?
This is where their mathematical prowess truly shines. They formalize this box selection process using a sophisticated induction argument, carefully building up their path scale by scale. They show that with high probability, they can select a set of well-separated boxes at each scale such that the Gaussian values associated with those boxes are independent and have sufficiently large values.
It's like proving that you can always find a diverse set of neighborhoods with great restaurants, no matter how interconnected the city's culinary scene might be.
That's a great way to put it. And this rigorous inductive argument is what allows them to establish those lower bounds on the last passage time for the BRW model, as stated in Theorem 3. They also leverage their earlier results on concentration inequalities to prove that the last passage time in the BRW model is tightly concentrated around its average value, as stated in Theorem 4.
So even in this highly correlated landscape of the BRW, they managed to demonstrate that the last passage time exhibits predictable behavior, thanks to their clever multi-scale construction and those powerful concentration inequalities.
Exactly, and their analysis of the BRW model not only provides deep insights into LPP in this specific setting, but also highlights the broader applicability of their multi-scale approach for tackling problems with hierarchical correlated randomness.
This deep dive has been a truly enlightening journey. We've seen how they've tackled the intricate challenges of LPP in both heavy-tailed and BRW environments, showcasing the power of multi-scale analysis, geometric insight, and probabilistic tools. Their work is a testament to the beauty and depth of mathematics, and it's clear that their insights will have a lasting impact on our understanding of random growth models and beyond.
I completely agree. Their work is both elegant and profound, and it opens up exciting new avenues for research. It's been a pleasure exploring this paper with you, and I'm sure our listeners will find their journey through these hierarchical landscapes just as rewarding.
Thank you for joining us on the deep dive. We encourage you to check out the show notes for links to the paper and other resources if you'd like to delve deeper into this fascinating topic. Until next time, keep exploring the world with curiosity and a thirst for knowledge. Hey there, ready to dive into some really cool math with me today?
Always.
Awesome. Okay, so today we're going to be looking at last passage percolation, but with a twist.
Yeah.
We're going to be adding in hierarchical environments.
Right.
So, fractals, logarithmic corrections.
Okay.
It gets pretty wild.
For sure.
We're going to be looking at a paper by Ganguly, Ginsburg, and Naum.
Okay.
And they kind of go through a bunch of different challenging scenarios that really kind of push the boundaries of what we normally think of with KPZ universality.
Right.
So for our listeners who, maybe haven't been thinking about last passage percolation recently, could you give us a quick recap of the basics?
Oh, yeah, sure. So imagine like a big grid, like a chessboard.
Okay.
And on each square of the chessboard, there's like a random number. It could be positive, negative, big, small.
Okay.
And you want to go from one corner of the chessboard to the other corner, but you're only allowed to go up and to the right. And as you walk along, you add up the numbers that you see. And the goal is to get the biggest possible sum.
Okay.
So that biggest possible sum, we call that the last passage time.
Okay.
And the path that gets you that biggest possible sum, we call that the geodesic.
Gotcha. So it's like you're finding the most rewarding route through some landscape.
Exactly.
Where every step has a different kind of payoff.
Yeah, you got it.
But in this paper, things get a lot more complicated, right?
Right.
Because of these hierarchical environments.
Yeah, so it's not just random numbers anymore. Like, now there's some underlying structure to those numbers. It's like if you were looking at a fractal, you zoom in, you see a similar pattern, but the numbers are changing in this very particular way.
Okay.
That creates this kind of multi-scale complexity.
Okay, so it's like this landscape we're trying to navigate. It's full of these hidden patterns, connections that we have to kind of untangle.
Exactly.
So what makes this so different from just the usual LPP setup?
Okay.
And why should we even care?
So in the usual LPP setup, we make some assumptions about how those random numbers are distributed.
Okay.
Like we might assume they have a normal distribution or something nice. But here we're looking at what we call critical environments.
Okay.
Where those assumptions break down.
Okay.
Where you might have like a few really extreme values that completely dominate everything.
Gotcha.
So it's like trying to navigate the city where you have like, traffic jams, but they're not just random.
Wow.
They're influenced by events happening at different scales.
Right.
Like you might have like an accident on one street.
Okay.
But then you have rush hour in a whole neighborhood.
Okay.
And then you might have some like citywide event.
Gotcha.
And all of these things are interacting to create these really complex traffic patterns.
So that's a perfect analogy.
Yeah.
Because we're trying to find like the most efficient way to navigate while all this stuff is going on. So the researchers in this paper, they look at two specific types of these critical environments.
Right.
One is with what they call heavy-tailed weight distributions.
Yeah.
And the other is with what they call the branching random walk, or the BRW.
Okay.
So let's start with the heavy tails.
Sure.
What exactly does that mean?
So a heavy-tailed distribution basically means that you're more likely to see extreme values than you would in like a normal distribution. So going back to the traffic analogy, it's like those traffic jams aren't just rare annoyances. They happen all the time, and they can be really, really bad.
So they're like a key part of how you have to navigate.
They're not something you can just ignore.
Right.
You have to plan around them.
Okay, so how do the researchers kind of approach this heavy tail problem?
They focus specifically on power law distributions, and particularly on a power law distribution with an exponent of, which is kind of a special point where things start to get really interesting.
Now, I remember exponent from, math class way back when.
Yeah.
But remind me what it means.
Yeah, so basically the exponent controls how heavy the tail is.
Okay.
So like a higher exponent means those extreme values are less likely.
Okay.
And a lower exponent means they're more likely.
So an exponent of 2 is kind of...
It's right on the edge.
Right on the edge.
Yeah, it's like the tipping point where things start to behave differently.
Okay, so they discover some pretty interesting stuff.
Yeah. Yeah, they prove this really cool lower bound for how the last passage time grows as you make the grid bigger. So normally in simpler LPP scenarios, you'd expect it to just grow linearly. Like you double the size of the grid, you double the last passage time.
Right.
But here they showed that it grows at least as fast as n log n to the 34 power.
Okay, well, hold on. Break that down for me.
Okay.
So N is...
N is the size of the grid.
The size of the grid. So as the grid gets bigger, the last passage time grows faster than just like proportionally.
Faster than linear.
Okay. Yeah. What's that log N to the 34 power?
So that's what we call the correction term.
Okay.
It's this extra factor that shows up because of the hierarchical structure because of those heavy tails.
So even though we're dealing with this crazy... city with unpredictable traffic, we can still say something about how the last passage time grows.
Right. We can still say something meaningful about the average behavior, even though there's all this randomness going on.
So how do they actually prove this lower bound?
Yeah. So they use this really clever technique called multi-scale construction, where they basically build a path step by step, and they focus on different scales of those traffic patterns.
So instead of just blindly going for the biggest weights, they're kind of strategically...
They're picking and choosing.
Picking and choosing.
They're picking and choosing.
Based on the hierarchy. Okay, so tell me more about this multi-scale construction.
Yeah. So imagine you start by focusing on the largest traffic jams.
Okay.
Like you build this kind of skeleton for your path around those, and then you zoom into a smaller scale.
Okay.
And you start looking at smaller traffic jams, and you kind of weave your path around those.
Okay.
But you always make sure you don't stray too far from that original skeleton.
So you're kind of balancing, taking advantage of the really big bottlenecks.
Exactly.
But also making sure that you're not getting bogged down.
Yeah, you don't want to get stuck in some little side street.
Exactly.
You want to stay on the main roads.
So the researchers, they actually formalize this by using what they call cylinders.
Right.
And they put these cylinders around the diagonal of the grid.
Yeah.
To kind of constrain the path.
Right. So the cylinders are like those main roads.
Gotcha.
They keep the path going in the right direction.
Okay.
But they're wide enough that the path can still capture those high-value weights.
Okay, so how do they choose the width of those cylinders?
Yeah, that's a really important question.
Yeah, it seems like a really delicate balancing act.
Yeah, if the cylinders are too narrow, the path might miss some good stuff.
Okay.
But if they're too wide, the path might become too zigzaggy.
Right, and lose its efficiency.
Exactly.
So there's like a sweet spot.
Yeah.
So is there a lot of complicated math going on behind the scenes?
Yeah, there's a lot of math involved in figuring out exactly what the optimal cylinder width is at each scale.
But it's not just about finding any path that satisfies these constraints, right?
Right.
They're trying to find the best path.
They want the path that maximizes the total weight.
Right.
So not just showing that a path with this lower bound exists, they're also showing that the last passage time is concentrated around its mean.
Okay.
Which means that even though there's randomness involved, the actual last passage time is usually pretty close to that average value.
That's good, because it seems like the whole thing is pretty chaotic.
Yeah, it's a very chaotic system. But we can still say some precise things about it.
But we've been talking a lot about this average behavior.
Yeah. Yeah.
What about those fluctuations
Right.
you were talking about earlier?
So those extreme values can definitely cause some big deviations from the average.
Okay.
And they actually prove a lower bound on those fluctuations as well.
Okay.
It's not the tightest bound, but it suggests that those deviations can be at least on the order of n.
So even though we know that the last passage time is usually close to its average,
right,
there's still room for
there's still some uncertainty.
some pretty big swings.
Yeah, it's not a deterministic system.
Right.
There's definitely some randomness there.
So it sounds like we're dealing with a much more unpredictable landscape
Definitely.
than with the classic LPP.
Yes,
Yeah.
and that's just one piece of the puzzle.
Okay.
We also have the branching random walk.
Okay, so let's shift gears and talk about that. Remind me how this model differs from the heavy-tailed case.
Okay, so remember how in the heavy-tailed case, those extreme values, they just kind of popped up randomly? Like those traffic jams could happen anywhere.
Right.
Well, in the BRW, things are a little more organized.
Okay.
It's like those traffic jams are influenced by events happening at a higher level.
Okay.
So instead of isolated traffic jams, you have rush hour affecting entire neighborhoods.
Go ahead.
You have these larger scale correlated variations in traffic flow.
Okay, so it's like the traffic patterns are being influenced by events happening at a higher level.
Exactly.
Okay. How does that change the game when it comes to finding the optimal path?
Yeah, so it adds this whole other layer of strategy.
Okay.
Now, you can't just blindly go after the areas with the heaviest traffic.
Okay.
Because those areas are likely to be clustered together.
Right.
You have to find a balance between hitting those high traffic zones and making sure your path doesn't get too convoluted.
So it's like you're trying to hit multiple busy neighborhoods, but you don't want to get
without getting stuck
in any one place.
Exactly.
We want to keep moving.
So does that multi-scale construction approach still work?
It does.
Yeah.
But it needs some adjustments.
Okay.
Because with those correlated weights, you have to be more careful about which scales you prioritize.
Okay.
So they lay out a modified multi-scale strategy that accounts for those correlations and makes sure that you're not just chasing after clusters of high weights that might lead you astray.
So it's like having a more sophisticated navigation system.
Exactly.
That's taking all this into account.
It's looking at the big picture.
What kind of results do they get with this?
Yeah, so they prove another lower bound on the last passage time.
Okay.
And they show that it grows at least as fast as n log n to the 12 power.
Okay. So even with the correlated weights, it's still
superlinear.
Superlinear.
Yeah.
Okay. But this time, the exponent
in that logarithmic term is smaller than in the heavy-tailed case.
Right.
Why is that?
So it basically highlights a key difference between the two models.
Okay.
In the heavy-tailed case, you could get lucky and find a massive traffic jam right along your intended route. But in the BRW, those high traffic zones are more predictable.
Okay.
You kind of have to navigate around them more strategically.
So those correlations are acting like constraints.
Exactly.
In a way.
They're limiting how much you can exploit those high weight areas.
So does that mean the optimal path through the BRW is smoother?
That's a good question.
Than the heavy-tailed case?
And that's something the paper doesn't explicitly address.
Okay.
It's one of the many open questions these models raise.
Yeah, I'm still really curious about, you know how wiggly those paths actually are?
It's a fascinating question.
And how that compares to the classic LPP.
Yeah, and it probably depends on the specifics of the hierarchical structure.
Right.
Like how strong those correlations are.
Okay, so we have these lower bounds on the last passage time for both of these cases.
Yeah.
But we also talk about the fluctuations.
Right.
Do they provide any insights into how much those paths can vary?
Yeah, they do. And this is where things get even more interesting.
Okay.
So for the BRW, they actually managed to establish both upper and lower bounds on the fluctuations.
Okay.
And they show that they're precisely on the order of n.
So we have a much clearer picture of the fluctuations for the BRW.
We know exactly how big they can be.
Okay. What's the significance of that?
It shows that there's a key difference between the two models.
Okay.
The heavy-tailed case with those unpredictable extreme values leads to more unpredictable behavior.
Okay.
Whereas in the BRW, those smoother correlated variations allow us to pinpoint the fluctuations more accurately.
It's like even though both models have these hierarchical structures, those subtle differences in how the weights are arranged can have a big impact on
They can have a huge impact
how those paths actually behave.
On how the whole system behaves.
That's really interesting.
Yeah.
So this is just like one part of what this paper does.
Yeah, they do a lot more.
They connect their findings to this question posed by Martin.
Yeah, back in 2002.
Back in 2002.
Yeah.
About when we should expect linear growth in LPP.
Right.
So tell me about that question.
Okay, so Martin was basically trying to understand when you can expect the last passage time to grow linearly with the size of the grid.
Okay.
And it was already known that if the weights have a finite second moment, which basically means they're not too spread out, then the last passage time will grow at least linearly.
Okay.
So a finite second moment guarantees at least linear growth.
Okay, so what was the question then?
The question was, is a finite second moment enough to guarantee linear growth?
Okay.
Or could it grow even faster? And for a long time, people thought that a finite second moment might be enough. But this paper shows that that's not always true.
Wait, so they found a counterexample?
Yeah, they found a counterexample.
Well, how did he do that?
They used their multi-scale construction for the heavy-tailed LPP.
Okay.
And they tweaked the weight distribution so that the weights do have a finite second moment.
Okay.
But the last passage time still grows super linearly.
So they broke that.
And they broke that link.
Link between a finite second moment and linear growth?
Exactly.
That's a big deal.
Yeah, it's a big deal.
So what are the implications of this?
It shows that even small changes to the weight distribution can have a huge impact on the behavior of the last passage time.
And it shows that their multi-scale construction is really powerful.
It's a powerful tool.
Yeah.
Not just for proving lower bounds, but for really exploring what's possible in LPP.
This is a lot to take in.
Yeah, it's a lot.
But there's even more, right?
Yeah, there's more.
This paper explores...
They do higher dimensions as well.
Okay, now you're just showing off.
It's not as bad as it sounds.
Okay.
The basic ideas translate pretty naturally to higher dimensions.
So instead of a 2D grid,
we're
now thinking about a 3D lattice or even higher.
Yeah, like a cube or a hypercube.
Yeah.
Yeah.
Okay, and our paths can now move...
They can move in more directions.
In more directions.
Yeah.
So in 3D, they can go...
Upright and forward.
Upright and forward.
Yeah.
Okay, and the last passage time is still...
It's still the same idea.
The same idea.
You want to maximize the sum of the weights.
Okay.
But now you have more freedom in how you choose your path.
And we're still interested in what happens when those weights have this hierarchical structure.
Exactly.
So instead of like 2D fractals, we're thinking about
3D fractals.
3D fractals or even higher.
Yeah.
I can't even imagine that.
It's hard to visualize.
Yeah. Does the math get a lot more complicated?
It can, but a lot of the core results still hold.
Okay.
Like those lower bounds on the last passage time and the insights about the fluctuations.
So the overall picture is consistent.
Yeah, the big picture is the same.
But are there any interesting like wrinkles that emerge?
Yeah. So one key difference is in those exponents that govern the logarithmic correction terms.
Okay.
So remember how in 2D, the last passage time for the heavy-tailed LPP grew like n log n to the 34 power?
Yes.
Well, in higher dimensions, that exponent changes.
Okay.
So the impact of those heavy tails depends on the dimension of the space.
So does the same thing apply to the BRW?
Yes. The exponent for the BRW also changes in higher dimensions.
Okay, so the paper actually presents formulas for how these exponents...
They give you the formulas.
...change.
Yeah.
Wow. So why should anyone care about these?
Yeah, that's a good question.
Higher dimensional scenarios.
So besides the mathematical beauty of it all, these models actually have connections to real-world phenomena. So, like, imagine a material growing, like a crystal forming, and the growth process can be influenced by impurities or imperfections in the material, which we can think of as those random weights.
So the interface between the crystal and its environment
it's like the path
is like the path
through the grid
that's navigating the weights.
Exactly.
And if those impurities have a hierarchical structure, like in these critical models, the growth of the crystal
it can be affected.
Can be really affected by
those logarithmic corrections.
Wow, so these ideas aren't just
They're not just abstract.
abstract.
They have real-world implications.
They have real-world applications.
Yeah.
So we're not just talking about paths on a grid.
It's not just math for math's sake. There's real physics here.
Gleaning insights into real physical systems.
Absolutely.
So what else does this paper talk about?
Well, one of the most interesting things is that it raises as many questions as it answers.
Okay.
So, for example, they provide these lower bounds on the last passage time, but the exact growth rate is still unknown.
So we know it grows at least this fast.
Yeah.
But it could be even faster.
It could be faster.
That's frustrating.
It's exciting.
But exciting.
Yeah, it's a mystery.
And then there's the question of the shape of the geodesic.
Right.
Which we've been talking about.
Yeah, we still don't know exactly what those paths look like and how they're affected by those hierarchical structures.
So this paper is kind of a launching pad.
Starting point.
For a whole wave of new research into LPP.
Yeah.
This has been a real eye-opener.
Yeah, it's a cool paper.
We've gone from like basic paths on grids to like these crazy scenarios.
Yeah.
With higher dimensions and heavy tails.
It's amazing what you can do with LPP.
Yeah, it's really cool.
Yeah.
So thanks for guiding me through all this. I think we'll definitely be revisiting these ideas as new discoveries emerge.
For sure.
But until then, keep exploring.
You too. Okay, so in the branching random walk, things are more organized. Like instead of just random traffic jams, you have rush hour affecting entire neighborhoods.
Okay.
So you have these like larger scale correlated variations in the traffic flow.
So it's like the traffic patterns are influenced by events happening at a higher level?
Exactly. It's like there's some underlying structure to the traffic.
Okay, how does that change the game then?
Well, it adds a whole other layer of strategy.
Okay.
Because now you can't just blindly go after the areas with the heaviest traffic.
Right.
Because those areas are likely to be clustered together.
Yeah, you don't want to just get stuck
exactly
in the middle of that.
You want to kind of spread out your bets a little bit.
So does that multi-scale construction approach still work in this scenario?
It does, but it needs some adjustments. Because with those correlated weights, you have to be more careful about which scales you prioritize.
Okay.
So they lay out this modified multi-scale strategy that takes those correlations into account.
Okay, so it's like having a more sophisticated navigation system.
Yeah, exactly.
That's considering not just the traffic density, but like the underlying patterns.
Yeah, like the relationships between different areas.
Yeah, okay. What kind of results do they get with this modified approach?
Well, they prove another lower bound on the last passage time.
Okay.
And they show that it grows at least as fast as n log n, 12.
Okay, so even with those correlated weights, the BRW still has superlinear growth.
It's still superlinear.
Okay, but this time that exponent in that logarithmic term is smaller than in the heavy-tailed case.
Yeah.
Why is that?
Well, it basically highlights a key difference between the two models.
Okay.
In the heavy-tailed case, you could get lucky and find a massive traffic jam right along your intended route. But in the BRW, those high traffic zones are more predictable.
Okay.
You kind of have to navigate around them more strategically.
So those correlations are acting like constraints.
Exactly.
They're kind of limiting.
They're limiting how much you can exploit those high weight areas.
Okay, so does that mean that the optimal path through the BRW is smoother than in the heavy-tailed case?
That's a great question, and actually the paper doesn't explicitly address the shape of the geodesic in either case.
Okay.
It's one of those many fascinating open questions these models raise.
Yeah, I'm still curious about whether those paths are more wiggly or less wiggly.
Yeah, it's a really interesting question.
In these critical environments.
And it probably depends on the specifics of the hierarchical structure.
Right, like how strong those correlations are.
Exactly.
Okay, so we've got these lower bounds on the last passage time for both of these cases.
Yeah.
But we also talked about the fluctuations.
Right.
Do they give us any insight into how much those paths can vary in these two models?
They do, and this is where things get even more interesting.
Okay.
So for the BRW, they actually managed to establish both upper and lower bounds on the fluctuation.
Hi.
And they show that they are precisely on the order of n.
So we have a much clearer picture of the fluctuations for the BRW.
We know exactly how big they can be.
Okay. What's the significance of that?
Well, it shows that there's this key difference between the two models.
Okay.
The heavy-tailed case with those unpredictable extreme values leads to more unpredictable behavior.
Okay.
Whereas in the BRW, those smoother correlated variations allow us to pinpoint those fluctuations more accurately.
So even though both models have these hierarchical structures, the subtle differences in how the weights are arranged can have a huge impact.
They can have a huge impact on how the whole system behaves.
On how the whole system behaves. That's really interesting.
Yeah, and this is just one piece of what they do in the paper.
Okay.
They also connect their findings to this question posed by Martin back in 2002 about the conditions for linear growth in LPP.
So remind me about that question.
Okay, so Martin was basically trying to understand when you can expect the last passage time to grow linearly with the size of the grid.
Okay.
And it was already known that if the weights have a finite second moment, which basically means they're not too spread out,
okay,
then the last passage time will grow at least linearly.
Okay.
So a finite second moment guarantees at least linear growth.
Okay, so what was the question then?
The question was, is a finite second moment enough to guarantee linear growth?
Okay.
Or could it grow even faster?
Okay.
And for a long time, people thought that a finite second moment might be enough. But this paper shows that that's not always true.
Wait, so they found a counterexample?
They did. They found a counterexample.
How did they do that?
They used their multi-scale construction for the heavy-tailed LPP.
Okay.
And they tweaked the weight distribution so that the weights do have a finite second moment.
Okay.
But the last passage time still grows super linearly.
So they broke that assumed link
They broke the link.
between a finite second moment and linear growth.
Exactly.
That's a big result.
It's a big deal. It shows that even small changes to the weight distribution can have a huge impact on the behavior of the last passage time.
And it shows that their multi-scale construction technique is really powerful.
Yeah. It's a really powerful tool for exploring what's possible in LPP.
Yeah, this is a lot to take in.
It is. It's a dense paper.
So they also do higher dimensions?
They do higher dimensions as well.
Okay, so instead of a 2D grid,
Yeah.
we're thinking about a 3D lattice, or even higher.
Yeah, like a cube or a hypercube.
Yeah, and our paths can now move in more directions.
Like exactly.
So in 3D, they can go upright and forward.
Yep, upright and forward.
And the last passage time is still the same idea.
It's the same idea. You want to maximize the weights along your path.
But you have more choices now.
Yeah, you've got more freedom.
Okay, and we're still interested in what happens when those weights have that hierarchical structure.
Exactly. We want to see how those hierarchical structures affect the last passage time.
So instead of 2D fractals, we're thinking about
3D fractals or even higher.
3D fractals or even higher. I can't even imagine that.
It's hard to visualize.
Yeah. Does the math get much more complicated?
It can get more complicated, but a lot of the core results still hold.
Okay.
Like those lower bounds on the last passage time and the insights about the fluctuations.
So the overall picture is still kind of consistent.
The big picture is the same, but there are some interesting wrinkles.
Okay, like what?
Well, one key difference is in those exponents that govern the logarithmic correction terms.
Okay.
So remember how in 2D, the last passage time for the heavy-tailed LPP grew like n? Log n 34. Well, in higher dimensions, that exponent changes.
Okay.
So the impact of those heavy tails depends on the dimension of the space.
Okay, so the same thing happens with the BRW.
Yeah. The exponent for the BRW also changes in higher dimensions.
Okay, and the paper gives us formulas.
They give you formulas for how those exponents change.
For how those exponents depend on the dimension.
Exactly.
That's really interesting.
It is. It's pretty cool.
So why should anyone care about these higher dimensional LPP scenarios?
Well, besides the mathematical beauty, these models have connections to real-world phenomena.
Okay.
So, like, imagine a material growing, like a crystal forming, and the growth process can be influenced by impurities or imperfections in the material, which we can think of as those random weights.
So the interface between the crystal and its environment is kind of like the path.
Like the path through the grid.
Navigating those impurities.
Exactly.
And if those impurities have a hierarchical structure, like in these critical models, the growth of the crystal can be really affected by those logarithmic corrections.
It can be strongly influenced by those corrections.
So these ideas aren't just abstract paths on a grid.
They have real-world implications.
They have real-world applications. Yeah. So we're not just talking about paths on a grid. We're
talking about real physical systems.
Gaining insights into how real physical systems behave.
Absolutely.
That's pretty cool.
Yeah.
What else does this paper talk about?
Well, one of the coolest things is that it raises as many questions as it answers.
Okay.
So, for example, they provide these lower bounds on the last passage time. But the exact growth rate is still unknown.
So we know it grows at least this fast, but
it could be even faster.
It could be even faster.
Yeah.
Okay, and we still have that question of the shape of that geodesic.
Yeah, we still don't know exactly what those paths look like.
Right.
And how they're affected by those hierarchical structures.
Yeah, so this paper is kind of launching pad.
It's a starting point for a whole wave of new research.
The LPP in these critical environments.
Exactly.
Okay, this has been a real eye-opener.
It's a really cool paper.
We've gone from, like, basic paths on grids to these crazy scenarios with higher dimensions and heavy tails.
It's amazing what you can do with LPP.
It really is. So thanks for guiding me through all this.
Of course, it's been a pleasure.
I think we'll definitely be revisiting these ideas as new discoveries emerge.
I'm sure we will.
But until then, keep exploring.
You too. Okay, so with directed polymers, imagine those paths aren't like fixed routes anymore.
Okay.
It's more like they're flexible chains.
Okay.
With a bit of wiggle room, you know, they can kind of explore different options before settling on the best one.
Okay, so I'm picturing like a path that's kind of fuzzy.
Yeah.
Like it's testing out different possibilities.
Exactly.
But what does temperature have to do with all this?
So temperature in this context controls how much the polymer can wiggle.
Right.
High temperature means lots of flexibility.
Okay.
Low temperature means it's closer to those rigid LPP paths.
So it's like a measure of how much randomness.
It's a measure of how much exploration the path can do.
Okay, why introduce this whole extra layer of complexity?
So it lets us model systems that are more dynamic, where the best path isn't like completely fixed.
Okay.
Like imagine a molecule moving through a fluid.
Okay.
It's constantly bumping into other molecules.
Right.
So its path is kind of unpredictable.
So directed polymers are like OPP, but with a bit of fuzz added in.
Exactly.
How do those hierarchical structures fit into this picture?
That's a great question. And this paper is really just the beginning of exploring directed polymers in these critical environments.
Okay.
They kind of lay out some open questions and challenges.
So give me a taste of those challenges.
Okay, so one thing is those correlations we talked about in the BRW. They become even more important with directed polymers because now that the paths can wiggle around, they're more likely to run into those correlated regions, which can really mess things up.
So instead of just finding the best route through a city with traffic jams, it's like we're trying to model a molecule navigating a turbulent sea.
That's a great analogy.
And it's constantly shifting.
Yeah, the landscape is constantly changing.
Okay, and what about those extreme values?
Yeah, those can really throw things off too.
Okay.
And with these flexible polymers, those extreme values might be even more influential.
How so?
Because the polymer can actually kind of seek them out.
Oh, wow, okay.
So it's like the molecule is actively searching for those areas of high energy.
Okay, so we're dealing with a whole new level of complexity here.
Yeah, it's a whole new ball game.
What kind of research needs to be done to really understand this?
Well, for one thing, we need new mathematical tools.
Okay.
The techniques we use for classic LPP and regular directed polymers, they might not be enough to handle these critical environments.
So we need like a whole new set of maps.
We need new tools.
And navigation tools. To figure this all out.
Exactly.
What about computational approaches?
Yeah, those are going to be crucial too.
Okay.
We need more powerful computational methods to simulate these systems.
Okay.
So we can actually see how they behave.
This paper's been really amazing.
Yeah, it's a great paper.
We've gone from like basic paths on grids to flexible polymers navigating turbulent seas.
It's been quite a journey.
It really has. And we've seen how these hierarchical structures can completely change the game.
They really shake things up.
Yeah. And we've even seen the limits of our current understanding.
Right.
There's still so much we don't know.
There's a lot of work to be done.
But that's what makes it so exciting.
That's the fun part.
So thanks again for guiding me through this deep dive.
It's been my pleasure.
It's been a real mind bender.
Yeah, it's definitely a lot to think about.
Yeah. But I think that's what we're here for.
That's what deep dives are all about.
To really push the boundary.
To explore the unknown.
Of our knowledge.
Exactly.
So until next time, keep exploring.
You too.
Welcome back, everyone. Today's deep dive is going to be pretty mathy.
Oh, yeah.
We're looking at last passage percolation.
Or LPP for short.
Right. LPP.
You're right.
LPP in hierarchical environments.
Yeah.
And it's sort of like...
You can think of it as finding like the best route through a city.
Okay.
With like totally random traffic. But instead of traffic, we're dealing with these random weights.
Okay.
Assigned to points on a grid.
Gotcha.
And so the goal is to find a path
Through this grid?
Yeah, that maximizes the total weight you pick up along the way.
That's really interesting.
And what makes this so cool is that it can be used to model all sorts of things.
Like what?
Like how interfaces grow in physics, or even how polymers behave in chemistry.
Wow. So we're not just talking about navigating a city here.
No. This goes way beyond that.
This is like fundamental stuff.
Yeah, really fundamental stuff.
So to make things even more interesting, the research we're looking at today focuses on two very specific types of environments.
Yeah.
Where those weights are distributed in really complex ways.
Yeah, and they get kind of wild.
Okay.
So the first one we have is weights following a power law distribution.
Okay.
And the second one uses a branching random walk to determine those weights.
A branching random walk.
Exactly.
Okay. And why are these environments so special?
Well, they kind of break the mold, you know?
What do you mean?
Like, they challenge our usual understanding of LPP.
Okay.
Like, we have these models like the Cardar-Parisi-Zhang theory or KPZ.
Right, KPZ.
And they work great for simple cases, but they don't really capture all the nuances of these hierarchical settings.
So our old tools aren't cutting it anymore.
Exactly.
We need something new.
Yeah, we need to up our game.
So where do we even begin with something like this?
Well, that's where multi-scale analysis comes in.
Multi-scale analysis.
She's like looking at the problem at different levels of zoom.
Okay.
You know, kind of like a fractal.
I see. So as you zoom in or out, you see these repeating patterns.
Yeah, exactly. And that's what makes these hierarchical environments so tricky.
Okay.
Because of these logarithmic correlations.
Logarithmic correlation.
Yeah, it means points that are far apart can still mess with each other.
Oh, that sounds messy.
Oh, it is very messy, and it makes things way more complex.
So it's not just about what's happening locally anymore.
Yep.
We have to consider these long-range connections, too.
Exactly.
Okay. I'm starting to see the challenge here.
Yeah.
So what are we even trying to figure out with this research?
Well, one of the big mysteries is figuring out the true growth rate of the last passage time.
Okay.
Which is basically the total weight collected along that optimal path.
Okay, so like in our city analogy, it's how much longer it takes to get across town as the city grows.
Yeah, but with all that crazy random traffic.
And those traffic jams are really unpredictable.
Oh, they are totally unpredictable.
Okay, so we're trying to find some order in all this chaos.
Exactly.
And what else are we trying to figure out?
Oh, another big question is how much the optimal path actually fluctuates.
Okay, what do you mean by fluctuates?
Like how much does it wiggle around if we change the weights or the size of the grid?
So how stable is our route through the city as things change?
Exactly.
We want to know if our best route today is still going to be the best route tomorrow.
Yeah, and that gets to the heart of randomness in these systems.
I see.
And how that randomness messes with the geometry of the paths.
So it's not just about finding the best path.
Nope.
It's also about understanding how reliable that path is.
You got it.
Wow, this is getting pretty deep.
Oh, we're just getting started.
Before we dive into the nitty-gritty, I want to take a look at the figures in the paper.
Yeah, they're pretty cool.
Especially figure 1.
Oh, yeah, that one's great.
It shows a simulated LPP geodesic.
Which is like the winning path on our treasure map.
I like that analogy.
Right.
And I love those skeletons of the path.
Yeah, you can really see how it grows across scales.
Yeah, collecting those weights.
And as you zoom in, those weights get smaller and smaller.
That visual really brings the multi-scale analysis to life.
It does.
But it also highlights a problem.
Oh, yeah.
Our old friend KPZ.
Right.
It doesn't account for those logarithmic correlations.
Nope. It just doesn't see them.
So it's like trying to use a street map to navigate a city with underground tunnels.
You got it.
We're missing a whole dimension of the problem.
Exactly.
So how do we get around that?
That's where this research comes in.
Okay. Tell me more.
Well, they use these theorems.
Theorems.
Yeah, like theorem 1, for example.
Give us that one, tell us.
It gives us a proven lower bound on the logarithmic correction term for the last passage time.
In the power law environment.
That's the one.
Okay, so we know for sure our travel time won't be any less than this as the city grows.
With those funky power law weights.
Exactly.
And what's really cool is the exponent they found.
Yeah, what is it?
It's 34.
34.
Yeah.
Why is that so special?
It's a big step toward figuring out the true growth rate of LPP.
In this critical case.
Right on.
Okay, so it's not just any lower bound.
No.
This one tells us something really important about how the system behaves.
It's giving us clues about the underlying dynamics.
Fascinating.
And this little difference in the exponent leads to an even bigger result.
Okay, hit me with it.
Theorem 5.
Theorem 5.
This one is a game changer.
Okay, I'm on the edge of my seat.
It challenges a long-held assumption in LPP.
What assumption?
Well, for a long time, folks thought
Yeah.
that if the weight distribution had a finite second moment,
Right.
then the last passage time would grow linearly with the size of the grid.
Okay.
But guess what? Theorem 5 proves that wrong.
No way.
It shows that even with a finite second moment,
Yeah.
the last passage time can still grow super linearly.
Mind blown.
I know, right?
So our intuition about these systems is totally off.
Totally off.
This is amazing.
And this actually answers a question
Oh, yeah.
that's been bugging mathematicians since 2002.
Wow. So we're talking about some serious mathematical progress here.
Absolutely.
So how do they even prove these crazy results?
Well, they used this clever combo of multi-scale analysis
Okay.
and some seriously slick probability arguments.
Probability arguments.
Yeah.
Okay, so they're not just playing with shapes on a grid.
Nope.
They're using some serious math.
You got it.
So walk me through it.
Okay, so they carefully construct this optimal path
Yeah.
by looking at different scales.
Right, those different levels of zoom.
Exactly. And they make sure it collects enough points from each scale.
So it's like building a tower
Kind of.
where each level has to be strong enough to support the next.
Yeah. And a big part of that is controlling the slope of the path segments.
The slope.
Yeah. If it zigzags too much,
Yeah.
it misses out on those valuable weights later on.
So it's a balancing act. You
Exactly.
got to collect enough points at each scale.
Yeah.
Like you can't be too greedy.
Right. You got to keep an eye on the big picture.
This is blowing my mind.
And that's where lemma 4.6 comes in.
Lemma 4.6.
It's like a secret weapon.
Okay, tell me more.
It shows how the slopes of different path segments cancel each other out.
Cancel each other out.
Yeah, so they can control the overall trajectory of the path.
So it's like a mathematical autopilot.
Yeah, something like that.
Keeping the path on course.
Exactly.
This is amazing stuff.
Oh, we're just getting warmed up.
Okay, well now I'm really intrigued.
Good.
Let's move on to that second environment.
The branching random walk.
Right.
You ready for this?
I'm all ears.
Okay, so remember the branching random walk, or BRW?
Yeah.
It's like a simpler version of the Gaussian free field,
Right, the Gaussian free field.
which is the super important model in physics.
Okay.
So understanding LPP in this context
Yeah.
has huge implications.
Gotcha.
Luckily, the BRW is much easier to analyze
Why is that?
because it's hierarchical by design.
Okay.
It's like it was made for multi-scale analysis.
That's convenient.
Very convenient.
So how do the findings in the BRW environment compare to the power law case?
Well, there's some key differences.
Like what?
Well, the power law environment has independent weights.
Right.
The BRW has these long-range correlations.
Oh, right. Those pesky correlations.
Yeah, so the path can't just jump around grabbing the highest weights.
It has to be more strategic.
Exactly.
It has to take advantage of those connections.
You got it.
And how does that change the results?
Well, for one thing, the lower bound is a bit weaker.
Weaker. How?
In the BRW case, it's n times log n to the 12, all divided by log n.
Okay, that sounds a bit less impressive than the 34 exponent.
It is a bit weaker, but
Yeah.
it's still pretty remarkable considering those long-range correlations.
Those correlations are really throwing a wrench in the works.
They are.
But that's what makes this research so exciting.
Absolutely.
And I noticed figure 3 in the paper really highlights these differences.
Oh, yeah. Figure 3 is a good one.
It shows how the optimal path in the BRW environment kind of sticks around in areas with high weight concentrations.
Right. It's got to milk those correlations.
Whereas in the power law case,
Yeah,
the path is more free to jump around.
exactly.
It's amazing how a subtle change in the weight distribution
Yeah,
can lead to such a different path geometry.
it really is.
So we've talked about the lower bounds.
Yeah.
What about those concentration and fluctuation results?
Yes, the concentration result.
Are things more predictable in one environment versus the other?
Well, that's where things get even more interesting.
Okay, lay it on me.
So theorems 2 and 4 prove that the last passage time is concentrated around its mean.
In both environments.
That's right.
So on average, things behave as we expect.
Yeah, but the scale of those fluctuations,
Yeah.
how much they wiggle around,
Right.
that's still a mystery.
So it's like we know the general direction,
Yeah,
but we're not sure how much the path might deviate from that path.
exactly.
And theorem 4 gives us something pretty cool for the BRW.
Oh, yeah.
Tight upper and lower bounds on the variance.
Which is pretty rare in these kinds of settings.
So we're actually getting a pretty clear picture of the fluctuations in the BRW environment
We are.
compared to the power law case,
It seems like the BRW is a bit more well-behaved.
despite those
I
correlations.
know, right? It's kind of counterintuitive.
And maybe a deeper understanding of these fluctuations
Yeah.
could help us understand LPP in hierarchical environments even better.
Absolutely.
Okay, well, this has been an incredible overview.
Just the tip of the iceberg.
But to really appreciate these nuances,
Yeah.
we got to dive into the math.
Let's do it.
So buckle up, everyone.
It's about to get real.
We're going deep into the proofs.
Can't wait. Okay, so let's unpack this proof for Theorem 1.
Yeah, the one with that crazy 34 exponent.
Right, that lower bound on the last passage time in the power law environment.
Okay, so how do they actually prove it?
It all boils down to multi-scale analysis.
Right, breaking the problem down into different levels.
Yeah, they define these cylinders and rectangles to represent different scales of the environment.
So like a set of nested boxes.
Exactly, each box capturing a different level of detail.
I like that analogy.
And there's this key parameter they use called zeta.
Zeta?
Yeah, it controls the separation between those scales.
Okay, so it's like how much we zoom in or out.
Yeah, they define it as 100 times the logarithm of n.
Whoa, lots of logarithms there.
Yeah, and n is the size of the grid.
Okay.
So zeta tells us how much we're scaling things as we move between levels.
Makes sense.
And then there's m,
Yeah.
which is the number of scales they consider.
Okay.
And it's roughly the logarithm of n divided by 10 times zeta.
So as the grid gets bigger,
Yeah,
we're looking at more and more scales.
exactly.
Okay. But why all the logarithms?
Those logarithms are crucial.
How so?
They capture the hierarchical nature of the problem.
Okay.
Remember those logarithmic correlations?
Well, the ones that make things so messy.
Exactly. Well, those logarithms are a direct result of those correlations. As n grows those logarithmic correction terms in the growth rate,
Yeah.
they're like a signature of this multi-scale behavior.
So those logarithms are like a map
Kinda?
guiding us through this complex web of scales and correlations.
Oh, yeah, a map through the mathematical wilderness.
I like that.
And they introduce another parameter too,
Okay.
lambda.
Lambda.
Yeah, and it's equal to the logarithm of n raised to the power of 14.
Another logarithm.
I know, right? They love their logarithms.
Okay, but what does lambda do?
It's a scaling factor for the size of the cylinders and rectangles.
Okay.
So as we move to larger scales,
Yeah.
we want to make sure the path collects enough points from each scale.
Right. Got to keep that path nice and heavy.
Exactly. And lambda helps ensure those cylinders and rectangles are big enough
Okay.
to capture enough points.
So it's like adjusting the size of our net
Yeah,
to catch the right amount of fish.
exactly. You got it.
Awesome.
And with these parameters,
Yeah.
they can show that with high probability there exists a path. That collects a good chunk of points from each scale.
So we're not just looking for any path.
Yeah.
We want a path that's loaded with points.
A super rewarding path.
And they call these sets of points V1 to VM
Right.
to represent the points collected at each scale.
Yeah, like containers for those valuable points.
Okay. And what do they do with these sets?
They show that these sets are big enough.
Big enough.
Yeah, big enough to give us that lower bound on the last passage time.
Okay, so we're building up this super path.
Exactly, brick by brick.
But how do we make sure it follows those slope constraints?
Good question. That's where lemma 4.6 comes in.
Right, the slope control lemma.
Yeah, it's a key part of the proof.
Okay,
It helps control those slope adjustments.
as we move between scales.
Exactly. Each time the path jumps.
Wow, so this lemma is essential.
Absolutely essential.
It keeps the whole construction from falling apart.
Yeah, it allows them to iterate over all those scales without losing control.
And that's how they get that impressive lower bound.
That's right. N times log n to the power 34.
Amazing.
And the cool thing is they can tweak this proof
Okay.
to prove Theorem 5.
The one that breaks the linear growth assumption.
That's the one.
Okay, how do they do that?
Remember how we said 34 is bigger than 12?
Yeah.
Well, that allows them to sneak in a logarithmic factor.
A logarithmic factor.
Yeah, into the tail of the distribution. So
Okay.
you get a finite second moment,
Right.
but the last passage time still grows faster than linearly?
So it's like they found a loophole,
Exactly.
a way to bend the rules without breaking them.
That's a great way to put it.
This is incredible.
It really highlights the power of subtle adjustments in math.
Yeah, sometimes the smallest changes
Yeah,
can lead to the biggest surprises.
absolutely.
Okay, we've covered a lot of ground with the power law model.
Yeah.
Let's shift gears back to the branching random walk.
Okay, you ready for round 2?
I think so.
Okay, so remember those long-range correlations?
Yeah, they make things tricky.
They do, and the biggest challenge is making sure
Yeah.
that the path collects distinct weights.
Distinct weights.
Yeah, as we move between scales.
Okay.
In the power law case, we didn't have to worry about that.
Right, because the weights were independent.
Exactly, but
Yeah.
in the BRW,
Yeah.
We could end up double counting weights if we're not careful.
So it's like navigating a maze where some paths lead you in circles.
Yeah, you got to avoid those dead ends.
Okay, so how do we stay on track?
Well, they use this fancy tree structure.
A tree structure.
Yeah, to represent the possible paths at different scales.
Okay.
Imagine a tree where each level is a different scale, and at each level we have 2 branches.
2 branches.
Yeah, representing different path options.
Okay, so we're making a choice at each level.
Exactly. And we always pick the branch that gives us the most weight.
Okay, so it's like a decision tree.
Yeah, a treasure hunt decision tree.
I like that.
But we have to make sure those branches lead to different treasures.
Yeah, no double counting.
And that's where things get really clever.
Okay, I'm all ears.
They construct those branches using disjoint sets of boxes.
Disjoint sets of boxes.
Yeah, from the BRW.
Okay.
By carefully choosing these boxes.
Yeah.
They make sure each branch is sampling from a different set of random variables.
So it's like we're dividing up the treasure map.
Yeah.
To make sure we're exploring new territory with each branch.
That's a great way to put it.
And that's how they prove Theorem 3.
That's right. The lower bound for the BRW.
The one with the n times log n to the 12 all over log n?
That's the one.
Wow, this is impressive stuff.
It is. And it shows how adaptable this multi-scale approach is.
Yeah, you can handle all sorts of crazy environments.
Even with those pesky correlations.
Now, what about Theorem 4?
Ah, yes. The concentration and fluctuation results.
That's the story there.
Well, Theorem 4 shows that the last passage time in the BRW case is surprisingly well-behaved.
Well-behaved.
Yeah, not only is it concentrated around its mean, but we also get matching upper and lower bounds on the variance.
Matching bounds.
Yeah, which is pretty amazing.
So we know exactly how much we can expect it to fluctuate.
Exactly. We've got it pinned down.
So in a way, the BRW, even with those correlations, is actually more predictable
than the heavy-tailed model.
That's counterintuitive.
It is, but that's what makes this research so cool.
Yeah. Sometimes the more complex systems actually have simpler solutions.
Exactly.
Okay, well, this has been an awesome journey.
Oh, we're just getting started.
Into the proofs of these theorems.
Yeah.
We've seen how they build up these arguments.
Yeah, using all these tools.
Multi-scale analysis.
Slope control lemmas.
Even fancy inequalities.
It's a mathematical masterpiece.
But before we move on,
can
we talk about how they prove those concentration results? Especially in Theorems 2 and 4.
Yeah. What are you curious about?
I'm interested in the tools they use.
To establish this concentration phenomenon, yes, the tools are just as important as the results.
Right.
In this case, they use something called the Efron-Stein inequality.
The Efron-Stein inequality.
It's a way to bound the variance of a function.
Okay.
Of independent random variables.
So like a way to measure how much things can change.
Yeah, essentially it tells us that if we understand how much a function changes when we tweak one of its inputs, we can control its overall variance.
So it's like a domino effect.
Kinda.
We change one thing and we see how it ripples through the whole system.
Exactly. And in LPP, the Efron-Stein inequality lets us see how much the last passage time changes when we tweak one of the weights.
I see.
And by using this inequality and the structure of the models, they can prove that the last passage time is tightly concentrated.
Around its mean.
That's right.
In both the heavy-tailed and BRW cases.
It's a beautiful application of this powerful tool.
So this inequality really helps to tame the randomness.
It does. It's like building a fence around the last passage time, preventing it from going too far astray.
This is amazing.
I know, right? Math is so cool.
It is.
And there's one more thing I want to mention about the lower bounds on the fluctuations.
In the heavy-tailed model.
Yeah. Remember proposition 5.2?
Yeah.
It gives us a lower bound.
Right.
But we think the true fluctuations are even smaller.
Okay.
Maybe by a polylogarithmic factor.
So there's still some mystery there.
There is.
Why is it so hard to pin down those fluctuations?
It's because of the interplay between those large infrequent weights and the overall geometry of the path.
Okay.
We know those big weights can really shake things up, but understanding how they affect the path's shape and how that contributes to the fluctuations is really tough.
So it's a dance between randomness and structure.
Exactly.
And we're trying to figure out the steps.
And those big weights are like rogue dancers. Throwing off the whole routine. And figuring out how much they disrupt things is key to understanding those fluctuations.
Okay, so we need to refine our analysis. Maybe bring in some new tools.
Maybe.
To crack this fluctuation code.
Exactly.
This is exciting stuff.
It is.
It feels like we're on the cusp of a major discovery.
I think so too.
But let's step back for a second.
Okay.
And talk about the bigger picture.
the big picture.
Yeah, you mentioned that LPP has connections to other fields.
Oh, yeah, it's connected to all sorts of things.
Like physics.
Yeah, physics, chemistry.
Even the study of random surfaces.
That's right.
So how do these abstract math concepts relate to the real world?
Well, one way is through interface growth.
Interface growth.
Yeah, like imagine a crystal growing in a solution.
Okay.
The impurities in the solution
Yeah.
create a disordered environment. And LPP can help us understand how those impurities affect the crystal's growth.
So those paths we've been analyzing,
Yeah.
they could represent how the crystal expands.
Exactly, navigating those obstacles.
That's pretty cool. It is.
And what about random surfaces?
Ah, yes. Those are connected through the Gaussian free field.
The Gaussian free field.
It's like a random height function,
Okay.
assigning a random value to each point on a surface.
So like a topographical map.
Exactly, but with random elevations.
Okay, I can picture that.
And LPP on the Gaussian free field
Yeah.
is like finding the highest path
Yeah.
between 2 points on that surface.
So like hiking through a random mountain range?
Exactly.
Cool.
And by studying LPP on simpler models,
Like the branching random walk?
yeah,
We can gain insights into those more complex surfaces.
that's right.
That's amazing.
It is. And the techniques from this paper
Yeah.
have implications far beyond these specific models.
So we're not just solving one problem.
No.
Developing tools that can be used.
To understand all sorts of complex systems.
In all sorts of fields.
That's incredible.
It is.
It's like we're opening up a whole new world of mathematical exploration.
Exactly.
And who knows what we'll find out there.
I can't wait to see what the future holds.
Me too.
But before we get too carried away,
Yeah.
let's focus on some of the big open questions.
The questions that are driving this research forward.
That's right.
Okay, so what are the next frontiers?
Well, one of the biggest questions is,
Yeah.
can we extend these techniques
Yeah,
to the full Gaussian free field?
right. The ultimate challenge.
Exactly. Remember, we focused on the BRW,
Yeah, as a simplified model.
but the Gaussian free field is the real deal.
So it's like we've climbed the first mountain,
Yeah.
and now we're staring up at Mount Everest.
And that's a whole different climb.
Okay, so what are the challenges?
Well, the Gaussian free field has these crazy correlations.
Right, even more complex than the BRW.
Oh, yeah. Way more complex. It's like
Yeah.
every point on the surface is connected to every other point.
Wow, so every decision we make
Yeah.
has these ripple effects throughout the whole system.
Exactly. It's like
Yeah.
trying to navigate a giant spider web.
Okay.
You touch one strand,
Yeah.
and the whole thing vibrates. So we might need some serious mathematical firepower
Okay.
to crack this one.
Like,
Maybe random matrix theory or integrable probability.
those sound intense.
They are, but they're designed to handle these kinds of correlations.
So it's like we're assembling a team of math superheroes
Yeah,
to take on this ultimate challenge.
I like that analogy.
And what else is on the horizon?
Well, there's also the connection to random planar maps.
Random planar maps.
Yeah, imagine a network of points and lines
Okay.
drawn randomly on a surface.
So like a random road map?
Yeah, something like that.
Okay.
And these random planar maps have these cool scaling limits.
Scaling limit.
Yeah, as you zoom out,
Yeah.
they start to look like these universal objects.
Like what?
Like the Brownian map.
The Brownian map.
Yeah, it's a fascinating object.
Okay.
And we think LPP models might have similar scaling limits.
So those random paths we've been talking about,
Yeah.
they might converge to these universal objects.
That's the idea.
Wow, so it's like those fractal patterns again?
Exactly, but on a much grander scale.
Oh,
And if we can prove those connections,
Yeah.
it would be a huge breakthrough.
a bridge between two different areas of math.
Exactly.
That's incredible.
It is.
And it just shows how interconnected math really is.
Absolutely. Even the most abstract concepts
Yeah.
can have surprising connections to the real world.
Well, this has been an amazing journey.
Oh, we've only just scratched the surface.
I can't wait to see what other mysteries LPP holds.
Me either.
Thanks for joining us on this deep dive.
Yeah, it's been a pleasure.
We hope you've enjoyed exploring these mathematical landscapes.
Yeah. And maybe you'll be inspired to learn more.
Until next time, keep those mathematical gears turning.
Okay, so we've seen some really cool stuff.
Yeah, this research has really pushed the boundaries
Definitely push the boundaries.
of our understanding of LPP,
For sure.
especially in these hierarchical environments.
Totally. But like any good research, it also raises new questions.
Oh, absolutely. It's like we've opened one door,
Yeah.
and now we see a whole new hallway
A hallway full of doors.
with even more mysteries behind them.
I love that analogy.
So what are some of those big open questions?
Well, one of the most exciting ones is, can we extend these techniques?
The multi-scale analysis and all that.
Yeah, all that good stuff.
To the full Gaussian free field.
Exactly. That's the holy grail.
The Gaussian free field.
Remember we used the branching random walk?
Yeah, it's a simplified model.
It was a good stepping stone.
Right. But the Gaussian free field is the real deal.
It's the ultimate challenge.
So we've climbed the Kitty Hill.
Yeah.
And now we're staring up at Mount Everest.
And it's a much steeper climb.
What makes it so much harder?
Those correlations.
Right. The Gaussian free field is all about correlations.
It's like everything is connected to everything else.
Yeah. No matter where you step.
Yeah.
It affects the whole system.
It's a very sensitive landscape.
I see.
So we need some new tools.
More powerful tools.
Yeah, to handle all that complexity.
Like what kind of tools?
Maybe random matrix theory or integrable probability.
Those sound pretty hardcore.
They are, but they're perfect for systems with crazy correlations.
Okay, so we're calling in the big guns.
Exactly. We need the best of the best.
This is getting exciting.
Oh, it is. And there's another interesting avenue.
Okay, tell me more.
The connection to random planar maps.
Random planar maps.
So like random networks.
Okay.
Drawn on a surface.
It's like a random road network.
Yeah, something like that.
Okay.
And they have these fascinating scaling limits.
Scaling limits.
Yeah, as you zoom out,
okay,
they start to resemble these universal objects.
Fractals.
Yeah, kind of like fractals.
Okay.
One example is the Brownian map.
The Brownian map.
It's a very special random object. And we think LPP models might have similar scaling limits.
So those random paths we've been studying.
Yeah. They might converge to these universal objects.
Wow, so it's like those fractal patterns again?
But on a much larger scale, we're looking at the global structure.
And if we can prove these connections,
yeah,
it would be a major breakthrough.
A bridge between two different worlds of math.
That's incredible.
It is, and it shows how interconnected math really is.
Absolutely.
But
even the most abstract ideas can have real-world implications.
Exactly. That's what makes math so powerful.
Well, this has been an amazing journey.
A wild ride through the world of LPP.
I've learned so much.
Me too.
And I can't wait to see what new discoveries are made.
The future of LTT is bright.
Thanks for joining us on this deep dive.
It's been a pleasure.
And we hope you'll continue to explore the fascinating world of mathematics. Welcome to a deep dive into last passage percolation in hierarchical environments.
Cool.
It's a fascinating paper, this one.
It is.
Like Bernoulli, Ginsburg, and Nahm.
Yeah, a real head scratcher.
Definitely.
But in a good way.
Yeah, the best way possible.
It really explores how things evolve in random settings.
Yeah.
Particularly like with layers of complexity, like hierarchical structures.
Right. And the paper focuses on last passage percolation, or LPP, in two different scenarios.
Okay.
Heavy-tailed environments and branching random walks.
Okay.
So it's like we're trying to navigate a landscape.
Yeah.
And the value of each point is random, and we're trying to find like the path through there.
Yeah, the most valuable path.
Yeah. That maximizes the total value.
Yeah, and the paper goes deep into proving lower bounds.
Right.
So figuring out the minimum speed at which things can evolve in these environments.
Interesting.
They use this concept of a geodesic, which is the optimal path through this random landscape.
So imagine like a grid where each cell has a random value assigned to it.
Okay.
LPP is like finding the highest scoring path through that grid from one end to the other.
It's connected to real-world phenomena, like interface growth in disordered media.
Okay.
Like you can think about crystals forming or fire spreading.
Right.
And we can actually model those using LPP.
So the path in LPP could be like the edge of a crystal growing or the leading edge of a wildfire.
Yeah, exactly.
It's not kidding.
So then the paper dives into heavy-tailed environments. And this is where things get a bit wild.
Okay, so tell me about that.
Yeah, so there's the Kardar-Parisi-Zhang, or KPZ universality class.
Okay.
And this usually describes how things evolve in LPP scenarios.
Okay.
But heavy-tailed environments have these occasional massive values.
Interesting.
Which throw off the KPZ predictions. So it's like you have a few hidden treasure chests in that grid that can just totally change the optimal path.
Okay, so the KPZ class is like the rule book.
Yeah.
But heavy tails are like...
They're like the rogue players that bend the rules.
How do the researchers account for these massive values?
Well, they use the Flory argument.
Okay.
And this kind of estimates the influence of those rare giant values on the geodesic. And it suggests that those large values are so influential that they will likely dictate where the optimal path goes, even if it means taking a slightly less direct route.
I see. So they're exploring the tension between grabbing those high values and staying on like an efficient path.
Exactly.
Interesting. And then they focus on a specific type of heavy-tailed environment.
Yeah.
Where the tail exponent alpha is equal to 2.
Yeah.
And this is where the hierarchical nature of the environment comes in.
Exactly. This is where it gets interesting.
The paper mentions criticality at this point.
Oh, yeah.
What's that about?
So think of it as a tipping point. Where those heavy tails start to dominate, and the hierarchical structure means the environment has a fractal-like quality. So similar patterns repeated at different scales.
So like imagine zooming into a fractal image and seeing similar patterns at each level.
Exactly.
How does that apply to this heavy-tailed environment with alpha equals 2?
So imagine a cake with layers.
Okay.
The bottom layer has the biggest, rarest values, while the top layer has smaller, more common ones. Each scale is like a layer of the cake.
Okay, delicious analogy.
Yeah.
So the researchers are trying to figure out how this layered structure with its unique value distribution at each scale affects the overall LPP.
Exactly. And this leads us to their key findings.
Right. Let's get into that.
Yeah. They prove 5 theorems,
each
establishing lower bounds on how quickly that geodesic can grow in these environments.
Let's unpack those theorems. Theorem 1 focuses on that heavy-tailed environment with alpha equals 2.
Right. Theorem 1 states that in this environment, the last passage time, which is denoted as L sub n, grows at least as fast as n times log n to the power of 3/4 divided by log n.
Wow, that's quite a formula.
Yeah.
Essentially, it's a minimum growth rate for the geodesic.
Right.
Based on the size of the grid and the properties of this heavy-tailed environment.
Yeah. To prove this, they use a clever multi-scale construction technique. Building a heavy path scale by scale. Imagine strategically choosing which values to include from each layer of that cake to maximize the final length of the path.
So they're meticulously building this path piece by piece. Carefully balancing the value they collect at each scale. While making sure they don't miss out on better opportunities.
Exactly.
Further down the line.
And they even use these subtle mathematical relationships called slope cancellations.
Interesting.
To maintain that delicate balance.
So it ensures that each step taken not only increases the path's value, but also keeps it on a trajectory to capitalize on future high-value points.
Precisely.
This is incredible.
It is.
Theorem 2 seems to shift the focus to concentration. What's that about?
So Theorem 2 proves that even though the environment is random, the growth of the last passage time is relatively predictable. It's like saying that even with the stock market's unpredictable fluctuations, there's an overall upward trend.
That's reassuring.
It is.
To know that amidst all this randomness, there's still a degree of order.
Exactly. And that predictability is crucial for understanding how these systems evolve over time.
Absolutely. But things get even more interesting.
They do.
When we move on to branching random walks.
Yes, branching random walks.
They sound a bit like family trees. Where traits get passed down.
You're spot on with the family tree analogy.
Okay.
Branching random walks introduce these long-range correlations. Meaning choices made early on can have ripple effects much later.
Interesting.
This adds a whole new layer of complexity to finding that optimal path.
So it's not just about grabbing the highest values at each step.
No.
It's about understanding how those choices will impact future possibilities.
Yeah, it's like a strategic game of chess.
Right.
Where every move counts.
Exactly. And because of this added complexity,
yes,
the lower bound, the researchers prove, in Theorem 3 for branching random walks, is weaker than the one for the heavy-tailed model in Theorem 1.
It is.
That makes sense. It's like navigating a maze where the walls keep shifting.
Exactly.
So what does Theorem 3 tell us?
Okay, so Theorem 3 proves that the last passage time, denoted as LBRW sub n, grows at least as fast as n times the square root of log n, all divided by log n.
Right.
Notice that the exponent on the log term is 1/2 here, compared to 3/4 in the heavy-tailed case.
Okay, so even with this added complexity,
Yes,
they've still managed to establish a minimum growth rate.
exactly.
That's impressive.
It is?
And then we have Theorem 4,
Okay.
which seems to echo Theorem 2 in terms of concentration.
You're right. Theorem 4 goes even further than Theorem 2.
Okay.
It not only proves that the growth of the last passage time is predictable in branching random walks,
Yeah.
but also gives us tight bounds on how much it can fluctuate.
Wow, so we're not just talking about the average growth rate.
No.
We're understanding the variability around that trend.
Exactly.
How do they achieve such precise predictions?
It comes down to the nature of correlations in branching random walks.
Okay.
While these correlations make path construction challenging,
Right.
they also dampen the overall fluctuations,
Interesting.
leading to more predictable behavior in the long run.
So the very thing that makes these environments more complex
Yeah,
also makes them, in a sense, more predictable.
exactly. It's a beautiful illustration of the balance between randomness and structure in complex systems.
A paradox.
Yeah,
But we're not done yet.
not yet.
Theorem 5 tackles a long-standing question in this field,
Oh, yeah.
one posed by Martin.
Martin's question.
Martin's question. It's all about figuring out the conditions needed
Yes.
for the limit shape, that long-term average growth rate to be finite.
Exactly. And it turns out that simply having a finite second moment
Okay.
for the weight distribution isn't enough.
Right.
Theorem 5 demonstrates this
Okay.
by constructing a specific weight distribution
Uh-huh.
that has a finite second moment but leads to an infinite limit shape.
So even if the average weight is well-behaved,
Yeah.
some extreme values can still throw off the entire system,
Exact.
preventing it from settling into a stable long-term growth pattern.
It's a reminder that averages don't always tell the whole story.
Right. Averages can be deceiving.
Yeah.
That's a key takeaway from this paper.
Yes.
Understanding the interplay between those rare, impactful events and the underlying structure of the environment is crucial
Yes.
for unraveling the mysteries of complex systems.
It is.
Absolutely. Now, the paper doesn't just stop at two-dimensional grids.
No, it doesn't.
It takes these concepts into higher dimensions,
Yeah.
which is where I think things get really mind-bending.
It's like taking that grid and layering it, creating a multi-dimensional lattice.
Yeah.
Where the path has even more freedom to explore and exploit those random values.
Okay, I'm trying to wrap my head around this. So
Yeah.
instead of a flat grid,
Yeah.
we're now picturing a 3D space, maybe like a lattice framework. And the optimal path is weaving through that complex structure,
Yes,
still trying to collect the highest values along the way.
exactly. And what's remarkable is that many of the insights from the two-dimensional case carry over to higher dimensions.
That's interesting.
For instance, Theorem 6 establishes a lower bound for the last passage time in a dimensional heavy-tailed environment with alpha equals 2.
So even in higher dimensions, those rare massive values continue to exert their influence.
Absolutely. Theorem 6 proves that in this d-dimensional setting,
Okay.
the last passage time grows at least as fast as n times log n to the power of d plus 1 over 4,
Right.
all divided by log n.
All right.
Note how the exponent on the log n term now depends on the dimension d.
Right. So the higher the dimension,
Yeah.
the faster the potential growth rate.
Exactly. It's like the path has more directions to explore and potentially more opportunities to stumble upon those high value points.
Right. And the researchers use a similar multi-scale construction technique
They do.
to prove this theorem.
Yes.
So it's like they've taken their toolbox for building heavy paths and adapted it to work in these higher dimensional spaces.
Exactly.
It speaks to the power and adaptability of their methods.
Yeah.
What about branching random walks in higher dimensions?
Oh.
Do those long-range correlations cause even more headaches?
They certainly do. Theorem 7 tackles this, proving that the last passage time for the d-dimensional branching random walk grows at least as fast as n times the square root of log n,
Okay.
all divided by log n.
All right.
Similar to the two-dimensional case, this lower bound is weaker than the one for the heavy-tailed environment,
Right.
reflecting the challenges posed by those long-range correlations.
So even in higher dimensions, branching random walks
Yeah.
continue to present unique challenges
They do.
in finding that optimal path.
Uh-huh.
But the researchers have still managed to quantify a minimum growth rate.
They have.
That's impressive. And Theorem 8
Okay.
seems to address concentration
Yes,
in this higher dimensional setting.
that's right. Theorem 8 proves that the last passage time for the d-dimensional branching random walk is concentrated around its mean,
Right.
with fluctuations of order n.
Okay.
This echoes Theorem 4 from the two-dimensional case,
Yeah.
highlighting the persistent predictability of these systems even as we increase the complexity.
So no matter how many dimensions we add or how intricate those correlations become, there's still a sense of order within these branching random walks.
Right.
Their growth might be slower than in heavy-tailed environments,
Yeah.
but it's still governed by predictable patterns.
Exactly.
This entire paper is a testament to the power of mathematical tools
It is.
to uncover hidden order within seemingly chaotic systems.
I completely agree.
Yeah, the researchers have provided us with a powerful framework for understanding the behavior of these complex systems at a fundamental level.
It's both elegant and insightful.
Yeah.
Demonstrating a beautiful interplay between geometric arguments and probabilistic tools.
It's like they've given us a new language to describe these phenomena.
Yeah.
A language that captures both the randomness and the structure that shape their evolution.
It is.
Before we wrap up,
Okay.
I think it's important to consider the broader implications of this research.
Yes, it goes far beyond LPP itself.
Right. So we've journeyed through this intricate landscape of LPP, heavy tails, branching random walks, and even ventured into higher dimensions.
We have.
But now let's talk about so what?
Okay.
You've unpacked these complex mathematical concepts beautifully.
Thank you.
But how does this all connect to the real world?
That's the million-dollar question.
Right. Why should anyone outside of theoretical mathematics care about these findings?
Right. So while this paper delves deep into the theoretical realm, its implications have the potential to ripple outward, impacting our understanding of countless complex systems.
Okay, let's explore some concrete examples.
Okay.
We touched on phase transitions earlier.
Yeah.
Could you elaborate on how this research could shed light on other areas of physics or chemistry?
Absolutely. Consider protein folding.
Okay.
Proteins are these incredibly complex molecules with intricate 3D structures.
Yes.
And the way they fold dictates their function. This process is influenced by an array of factors, many of them random, and could be modeled using approaches inspired by LPP.
So by understanding how paths optimize themselves in those hierarchical random environments, we might gain new insights into how proteins find their optimal configurations.
Exactly, and the implications are huge.
Right.
Understanding protein folding is crucial for drug development, materials science, and even unraveling the mysteries of diseases like Alzheimer's, which are linked to protein misfolding.
That's incredible. So this seemingly abstract mathematical concept could be a key to unlocking breakthroughs in medicine and beyond.
The possibilities are vast.
Right.
Let's shift gears to computer science and algorithm design. Many algorithms involve navigating complex networks, searching for the most efficient path.
So the techniques used to find those heavy paths in LPP could potentially be adapted to design more efficient search algorithms.
Precisely, whether it's searching through massive databases, optimizing logistics networks, or even navigating the complexities of financial markets.
Interesting.
These ideas could lead to more effective solutions.
And let's not forget about climate modeling.
Yes.
We discussed how this research could help us understand systems near critical points.
Yes.
That sounds incredibly relevant to predicting and mitigating climate change.
Absolutely. Climate models are incredibly complex. And understanding how small changes can cascade into large-scale shifts is crucial.
Right.
The insights from LPP and hierarchical environments could offer valuable new perspectives on these dynamics.
This is truly mind-blowing.
It is.
We started with this seemingly abstract mathematical concept.
Right.
And now we're talking about potential applications that could reshape medicine technology and even our understanding of the planet.
It's exciting.
Yeah. This paper has definitely been an eye-opener.
Yeah.
But I keep coming back to Martin's unsolved problem about the conditions for a finite limit shape.
Yeah.
Do you think this research brings us any closer to solving it?
That's a great question.
Yeah.
While it doesn't directly solve Martin's problem, it offers valuable clues by showing that a finite second moment isn't enough.
Yeah.
For a finite limit shape, they've narrowed down the search space.
Right.
Their multi-scale construction technique could also be a powerful tool for further exploration.
So it's like they've handed us a more powerful lens to examine this puzzle. We might not have the complete solution yet, but we have a clearer path forward.
Exactly. And perhaps building upon this foundation, future researchers will crack Martin's problem wide open, unlocking even deeper insights into the nature of complex systems.
This has been an incredible deep dive.
It has.
We've explored intricate theorems, envisioned real-world applications, and even pondered the mysteries of unsolved problems.
We have.
But as we wrap up, I want to leave you with one final thought.
I'm intrigued.
We've focused intensely on finding the optimal path, the geodesic, through these random landscapes. But what about the other paths? The ones that aren't optimal. Could they hold valuable information? Or offer alternative strategies for navigating complexity?
That's a fantastic point. It challenges us to think beyond optimization. And consider the value of exploration and diversity. Perhaps by studying those less traveled paths, we might uncover hidden connections, new solutions, and a richer understanding of the systems that shape our world.
That's the beauty of scientific inquiry.
It is.
The constant questioning, exploring, and pushing the boundaries of what we know.
Yeah.
This deep dive is just one step in that endless journey.
It is.
So keep diving deep and keep those questions coming until next time.
Sounds good.
Okay, so where were we?
We were talking about how these insights from LPP could impact other fields. Right, like maybe physics, chemistry.
Yeah, like think about phase transitions.
Okay.
This research could help us understand how systems behave near those critical points.
So like the point where water turns to ice?
Exactly. Or where a metal becomes magnetic.
Right. Those tipping points where the system undergoes a dramatic change.
And these phase transitions pop up everywhere in nature.
Okay, so how does LPP tie into all of this?
Well, the models used to study LPP can also be used to analyze phase transitions.
Interesting. So the same mathematical framework that describes how those paths evolve could also shed light on how systems transition between different states.
Exactly. And understanding those transitions is crucial in so many fields.
Right, like predicting earthquakes or developing new materials.
Absolutely. This research could have far-reaching consequences.
So it's not just about those paths and those random values.
No, it's about understanding the fundamental principles that govern complex systems.
Yeah, the underlying mechanisms that drive those large-scale changes.
And those insights can then be applied to a wide range of phenomena. This is really making me appreciate the power of theoretical mathematics.
Yeah, it's not just about abstract equations.
Right. It's about providing a language and a set of tools to understand the world around us.
And to potentially solve some of the biggest challenges we face.
This deep dive has been a real eye-opener.
It has been fascinating.
But before we get too carried away, I want to make sure we're not losing sight of the math.
Of course. Let's dive back into the details of the paper.
Right. Let's talk about those specific theorems.
Okay, so we left off with Theorem 5, which tackled Martin's question about the conditions for a finite limit shape.
Right, and they showed that a finite second moment isn't enough.
Yeah, it was a surprising result.
It really highlights the subtle interplay between those rare events and the overall behavior of the system.
Now, Theorem 6 shifts the focus to higher dimensions.
Okay, things are about to get even more mind-bending.
So imagine instead of a flat two-dimensional grid, we're now dealing with a three-dimensional lattice.
Okay, I'm picturing like a framework of interconnected points.
Exactly, and the path now has more freedom to move around.
Right, and go up, down, left, right, forward, backward.
Exactly, and Theorem 6 establishes a lower bound for the last passage time in this higher dimensional setting.
So it's like they've extended their analysis to a more complex environment.
Precisely, and what's interesting is that the lower bound changes.
How so?
Well, in the two-dimensional case, the lower bound depended on n and log n, but in higher dimensions, it also depends on the dimension itself.
So the growth rate is potentially even faster in higher dimensions.
Exactly. It's like the path has more space to explore.
And more opportunities to find those high value points.
Precisely. Theorem 6 captures this by incorporating the dimension into the formula.
Wow. So even as we increase the complexity, the researchers are still able to provide these quantitative bounds.
It's a testament to the power of their mathematical tools.
Absolutely. Now, what about branching random walks in higher dimensions?
That's where Theorem 7 comes in. It tackles those long-range correlations.
Right, those ripple effects that made branching random walks so challenging.
And it proves a lower bound for the last passage time.
In this higher dimensional setting.
Exactly. But similar to the two-dimensional case, this lower bound is weaker than the one for the heavy-tailed environment.
So those correlations still pose significant obstacles.
They do, but the researchers have managed to quantify their impact.
That's impressive given the increased complexity.
It is. And then we have Theorem 8.
Okay.
Which addresses concentration in higher dimensions.
So it's like Theorem 4.
Yeah, it's the higher dimensional counterpart.
Okay, what does it tell us?
It proves that the last passage time for the d-dimensional branching random walk is concentrated around its mean with fluctuations of order n.
Okay, so even in this more complex setting,
yes,
we still see that predictability.
Exactly. Those long-range correlations might make things tricky. But the overall behavior is still governed by these statistical laws.
That's really remarkable.
It speaks to the underlying order that exists even within these seemingly random systems.
This entire paper is like a symphony of mathematical elegance.
I like that analogy.
Yeah, it's a beautiful blend of rigorous analysis and deep insights into the nature of complexity.
And it leaves us with so many exciting questions to explore.
Absolutely. But before we get lost in those questions, I think it's time to step back.
Yeah.
And consider the broader implications of this research.
So what?
Exactly. How does all of this connect to the real world?
That's the question we need to answer next.
So we've been talking about how this research could have implications beyond theoretical mathematics.
Yeah, like real-world applications.
Right, but where do we even begin?
Well, one area that comes to mind is computer science.
Okay.
Specifically, network routing.
So like the internet.
Exactly. Imagine you have a network with millions of nodes, and you need to find the most efficient path to send data from one point to another.
That sounds like a pretty complex problem.
It is, and it's very similar to the problems studied in this paper.
Right, like finding those optimal paths through random landscapes.
Exactly. The insights from LPP could help us design more efficient routing algorithms.
So we could potentially make the internet faster and more reliable.
Exactly. That's just one example.
What about other fields?
Well, this research could also have implications for finance.
Okay, how so?
Well, think about stock prices.
Right, they fluctuate randomly.
Exactly, and investors are always trying to find the optimal time to buy or sell.
So it's like finding that optimal path through a random landscape of stock prices.
Precisely, the tools and techniques used in this paper could be applied to financial modeling.
Interesting. So we could potentially use these insights to make better investment decisions.
It's definitely a possibility.
Now, I know we've been focusing a lot on the practical applications.
Yeah.
But I want to circle back to the theoretical side for a moment.
Okay.
You mentioned earlier that this paper leaves us with some exciting questions.
Oh, yeah, there's so much more to explore.
Like,
well, for one thing, the paper focuses on specific types of hierarchical environments.
Right, like those heavy-tailed environments with alpha equals 2.
Exactly, but what happens when we change those parameters?
Yeah, what about other types of hierarchical structure?
Or different weight distributions.
Right, there's a whole universe of possibilities out there.
And exploring those possibilities could lead to even deeper insights.
Into the nature of complex systems.
Exactly, this paper is just the tip of the iceberg.
It's like they've given us a map. But we've only just begun to explore the territory.
And who knows what we might discover along the way.
That's the beauty of scientific research.
It is.
The journey is just as important as the destination.
Absolutely, and sometimes even more so.
Well, this has been a truly fascinating deep dive.
It has been a pleasure.
We've delved into the intricate world of LPP, explored its connections to other fields, and even pondered the mysteries that remain unsolved.
And we've only just scratched the surface.
Right. There's so much more to discover. So until next time, keep diving deep.
And keep asking those tough questions.
That's what it's all about.
It is.